Allora, benvenuti a questa seduta di laurea magistrale. Lavoriamo due gruppi, in realtà un gruppo più una persona di due lauree diverse, quindi sia la laurea in ingegneria automatica, ovvero control engineering, che la laurea magistrale in ingegneria, scusate, in artificial intelligence e robotics, quindi intelligenza artificiale e robotica. Avremo uno studente che è stato aggregato a questa sessione per motivi amministrativi, diciamo. Abbiamo quindi 11 studenti che sentiremo nell'ordine e poi un altro studente a conclusione, in ordine alfabetico. Ogni studente farà la sua presentazione in inglese perché le lauree sono tutte erogate in inglese, quindi anche la discussione sarà in lingua inglese. E ci saranno poi delle domande, alla fine faremo la proclamazione dopo aver fatto una discussione interna, per cui alla fine di queste 12 presentazioni vi chiederemo di lasciare l'aula per poco tempo, poi vi richiamiamo e facciamo la proclamazione tutti insieme. Ok? Quindi questa è l'organizzazione. Cominciamo con il primo degli studenti di Control Engineering, che è Giovanni Antonucci. È andato in bagno. Fantastico. Allora lo metteremo al secondo posto. So the next one is Bahar Barsegar. Yes, yes. She's presenting a thesis on computational methods for cognitive flexibility. His advisor is Professor Christian Napoli. So you have 15 minutes, okay?
Good afternoon. Today we are going to talk about, explain computational methods for cognitive flexibility. And as an introduction to cognitive flexibility, we want to say that cognitive flexibility is one of the executive functions of the brain. Executive functions include high-order cognitive abilities like working memory, inhibitory control, and planning, reasoning, problem solving, and cognitive flexibility is one of them. So executive function of the brain has three latent variables, and shifting, updating, and inhibition. And the term flexibility is related to the shifting. As a common definition for cognitive flexibility in the literature, we find this definition. It is the ability of people to rearrange information depending on the changing situation. So if we want to explain some features of these, cognitive and behavioral flexibility regulate the thoughts. And also with cognitive flexibility, we reconstruct information in a different ways. And also cognitive flexibility is related to attentional processes, and people are able to adapt themselves to new and unexpected conditions. Why this topic, cognitive flexibility, is important? We try to check this topic for two different things: cognitive flexibility role in children, and also how cognitive flexibility is related to disorder. Cognitive flexibility role has a great impact on children, as it improves academic achievement, employment success, successful transition into adulthood, and also improves writing and reading comprehensions, and is related to creativity, and also makes better attention and behavioral regulations, and also make and cognitive flexibility is related to character in different age groups like preschool children. And also in the recent studies, they have found that cognitive flexibility and math are related, means the people are or children are more efficient in mathematical way if they have high cognitive flexibility. So they get higher math scores if someone has a high cognitive flexibility. And also it is related to different disorders, and Parkinson's disease, for example, and amyotrophic lateral sclerosis, ALS, and different kind of things. The most important one, attention deficit or hyperactivity disorder, which to cognitive flexibility, and another one, transfer utilization deficiency. Children transfer a strategy but not its benefit. They learn something, but they have problem to reuse the strategy or the learned things. And other disorder like obsessive compulsive disorder that makes obsessive thoughts and compulsive behaviors. So this topic is related to different kind of disorders. And if we want to mention some of them, for example, if I compare them, for example, we have different categories. For example, Parkinson's disease in a category of neurocognitive disorders. And what is the cognitive and behavioral appearance of flexibility deficit in this kind of disorder? Is excessive cognitive rigidity. And for example, in attention deficit or hyperactivity disorder, the deficit is in attention in these kind of people. So in recent studies, we have found that this is an interesting topic for more investigation. In here, we are going to present some assessment tools to how to measure cognitive flexibility. The most popular one, all the studies are going to use this kind of test. Wisconsin car sorting test is a kind of test that participants are presented in two ways, manual way and computerized way. And some target or target cards are presented to participant or test taker. And also some, they're presented some response card. They have to sort the cards based on three categories: color, shape, and a number. So also there are in a manual way, the examiners tell participants whether their matches are right or wrong. Actually, they give the feedback without providing the category, means it is color, shape, or number. So we have some categories and we have some responses, and we have feedback, positive or negative. And another one, we are going to use this test in later. So another assessment tools for measuring cognitive flexibility is trail making test. It has two parts, A and B. In A, the participant have to connect 5 encircled numbers together to each other. And in test B, they have to alternate between numbers and letters. For example, 1A, 2A, and different conjunctions in a given time. So the measure of shifting or flexibility here is the total time that taken in part B minus the total time taken in the part A is a measure of as a result of this test. So another one is semantic verbal fluency. The participants have to say as many words as possible for two categories like fruits and animals, or start with a specific letter for 60 minutes in a specific amount of time. And as a score, the correct scores are the total number of the correct words as a result of this test. So the last one is 5-point test. They have some we will see some points on the screen. It's a paper and pencil test actually, and they have to. They have some points symmetrically organized dots. Actually, they have to connect each other, make pattern, meaningful pattern, and with drawing straight lines. So the score is total number of correct design. These are the tests for measuring cognitive flexibility, but we want to use only WCST in a model, computational model. So what is computational methods? Computational methods formalize covert cognitive processes and the way covert cognitive processes interact by mathematical expression. Actually, computational methods are working on latent variables, and we know observed variables, but they are working on latent variables. that reflect effect of cognitive, covert cognitive processes. And there are two representation and computational methods actually represent by neural networks and mechanistic models. But we are working on mechanistic models, and the reason is that in a comparison, neural networks use a very large number of latent variables, so they have precise estimation. But mechanistic models present a small number of latent uses, a small number of latent variables, so they are psychologically interpretable. So, as a conclusion, mechanistic models are the best approach for assessment of covert cognitive processes on WCSD as one of the measurement tools for cognitive flexibility. This approach called computational neuropsychology. So the computational methods are working on the result of the viscosing card sorting test, the test. So participants in test are going to sort some cards based on some rules. This test has some errors. Some errors happen into this test as a result of this test. Perseveration error and set loss error. Perseveration error refers to wrong repetition of a category, means color, number, or shape, after receiving a negative feedback, and SLE, set loss error, is wrong switches to a category after receiving a positive feedback. Why we want to focus on these two errors? Because with an increased PE or SLE, we will have cognitive inflexibility. So the study of these two errors reveals something for us. So, with the help of computational modeling, they can determine more undetectable part of covert cognitive symptoms or these kind of things, and we want to investigate how computational modeling contribute to the growth of the next generation of the neuropsychological assessment methods. So there are three mechanistic models, and attentional updating or learning model and cognitive reinforcement learning, which the parallel reinforcement learning was the best in the recent studies. Attentional updating model is based on something participant creates some attentional prioritization, APs, or attentional weight. These two are the same, but in the recent studies we will see these two, and they are the same but in different words. So high AP of category means result in a high probability of selecting that category on a specific trial. For example, if on trial T we have color as a correct answer, the probability of selecting color in the next category will be high. So, based on the feedback, positive or negative, we have we create something, attentional or attention weight. Attention weight or AP after positive feedback will increase and after negative will decrease. So, as a result of an increase, probability of selecting category means repetition of a category becomes more likely, and after decrease, a switch to select another category becomes more likely. So this is on the top we see the one trial of computerized WCSD, and feedback goes to the model, and we find some response probability, and what is the possible the participant is going to choose, for example, number response 1 or category, color or number or shape. So we will see some parameter F, D, and P here. They have meaning. P is the sensitivity parameter, and is related to how quickly attention changes in response to positive and negative feedback. D is this decision or choice consistency, and F is attentional focus. And we have something like attention weight vector, which create based on the feedback here. And then we have a feedback signal vector and a matching vector, and these kind of things to finally to reach to a mathematical expression for this model. There are something that the rewarded means the participant received a positive feedback. A punished means they receive a negative feedback, and finally the probability of selecting something. What is important here is related to two parameters. F, attentional focus, and D, another parameter which contribute to the probability. Low F means attention should split between possible. For example, we have a case, number and color would be two possible answers. With low F, attentional focus, attention should be split between two categories. With high F, attention dedicates to correct category. With low D, the answers are more random. For example, with high D are more deterministic, constraints on attention. So these are an attention weights on positive feedback, attention. For example, one participant answered color category in many trials, means that he or she can recognize color category very well. So attention weight for color category will be high. For that, the probability of selecting color category or another category will be high in the next trials. As an example, we will see that. For example, a target card is 4 red cross, and the participant chose 3 yellow cross, which is wrong, received wrong feedback. Means feedback is ambiguous, means we have two possibilities, means shape is not the correct answer. The possible answer are shape, or number or color, because shape is not the correct. So in this case, if we I want to say F and the meaning of the attentional focus, if we choose F small, attention should be split between color and number. And but there is an issue that we see in the case participant answered color category in several trials. Low attention focus F will reduce the attention to the color. Even color is the color category, means the participant know color well. If we choose F, a big number, so maximum attention should be for the color category, because F is presented here as a feedback, and so with high, we can have, S means feedback, we can have the correct attention. Another one is the cognitive reinforcement learning is based on the framework of reinforcement learning, It's based on feedback prediction. Here is feedback prediction, goes into the model and we find something, but the parameters are different. We have tau, omega, and alpha. Alpha is the cognitive learning rate, and these are a retention rate, and this tau is something different, and we will see. And because the parallel reinforcement learning model was the best, because it's parallel, there is a hypothesis that participants learn at 2 levels, category level or response level. What does it mean? It means in category level, when participants receive a positive feedback, repeat the category on the next trial, and they're thinking, yes, this category is correct, and after receiving positive feedback, they repeat. After receiving the negative feedback, they switch between categories. For example, they choose color, they receive a negative feedback. For the next trial, they choose, for example, number, because they are thinking something is wrong. And in response level, after receiving positive feedback, they repeat a particular response. For example, they chose response 3, and when they positive, maybe they're going to choose again response 3 as a correct. And for negative feedback, they avoid previously selected response. Is 3 is they receive, and after choosing a response, they receive a negative. They avoid to choose again that response. So this is a parallel model we see that the feedback prediction goes to the into the model. We have two levels. Parallel level is combination of a cognitive and sensory motor oral. This is the category level learning on the top, and on the below we have response level. So finally, we integrate the feedback prediction, and the feedback prediction goes to the response probability. It is the softmax function that wants to compute the response probability based on the integrated feedback prediction. So in this model, we have something, feedback prediction. In sensory motor RL, it uses feedback prediction for the execution of the responses, and for cognitive RL, uses feedback prediction for categories. So after receiving a positive feedback, feedback prediction for executed response or category will increase, and for negative one decrease. So after positive feedback, the probability of executing again that responses or category means actually repetition will be more likely, and switch will be more likely after negative feedback. So this is the mathematical relation between the parameters, the retention rate, cognitive feedback predictions. For example, we have feedback prediction here, retention rate, and these are going to transfer from one trial to the another trial with different strengths. And finally, we have this is the integrated feedback prediction for response and categories. And finally, the softmax function use this formula to find the response probability. And the important things are the parameter here, like retention rate and cognitive learning rate. High values of omega C, which is cognitive learning rate, because we have two learning rates, cognitive and sensory motor, represent a strong impact of previous feedback prediction. Okay, I'm going to prediction on current responding means increased retention rate means more information retained from the previous feedback. So higher learning rate means a strong cognitive learning. So, why parallel was the best model? Because our criteria is how well they predict trial responses. So, for example, best estimation of the latent variables. So we can say that model is the best reveal the covered cognitive symptoms and processes. And we are some case study on VSD with that worked on two diseases, Parkinson and ALS. And they have found that in Parkinson disease, the patient have increased cognitive retention rate, which leads to inflexibility of thoughts, and also reduced sensory motor retention rate. And we will see the cause, which leads to impaired response learning. And in the first one, in the left image, we have a bradykardia, which is the result of increased cognitive retention rate. And also we have see something in terms of effect of cognitive learning rate after positive feedback. We will see patient with PD in the left picture received reduced cognitive learning rate, and for the patient with ALS, we will see increased inverse temperature is a parameter that plays a role in the probability that makes the probability attenuate or emphasize or something. So we will see. Okay, as there are some challenges, and we have to consider the computational method should be validated, and should be validated to, and also investigate the clinical validity of the computational modeling. The modeling is important. As a conclusion, we can say that we're presenting that computational psychology have the potential to reveal some cognitive symptoms, as we see, for example, in patients with PD and ALS, they have when they have increased or reduced of some parameter, learning rate or retention rate. So we can say that parallel reinforcement learning was the best and provides a new theoretical perspective on card sorting. And so we can say that computational neuropsychology offers a potential to use for neuropsychological assessment. And okay, thank you. This is just based on the recent studies, and they have some healthy person, they have some patient with PD, and just a study. I used the result of the recent studies in this field. But I personally worked with something with the professor, and it was something different. We are going to generate an AI-driven psychometric test, like WCSD. And
okay, thank you then. On task scheduling in assembly line with deep reinforcement learning. His advisor is Professor Cristo Liberale.
Okay. So, non ce l'ho. Bisogna switchare da questo punto.
Tanto mettiamo poi vogliamo qua toglierlo. Così.
Non c'è un cosettino per ridurlo, sembra. Non so, almeno da vederlo io non mi sembra.
Questo qui? No, interrompo.
Per mandare sulla barra. Ah, ok. Sì, ci sta il titolo.
Non c'è.
No, nomi degli annotatori. No, non ci sta. Okay. Sì, dovrebbe esserci il titolo, dico la data. Okay. 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 So, task scheduling in assembly line with deep reinforcement learning. In recent years, industrial processes have become more complex and subject to uncertainty and delays. And on this purpose, there is a necessity of a more flexible manufacturing system. But classical control optimization-based techniques do not give enough flexibilities, and machine learning has become the cornerstone of the Industry 4.0. Then, inspired by the SESAM project, where it is proposed to implement an intelligent agent to support the scheduling operators in real-time real scheduling, we propose the problem of controlling an industrial assembly line, where the objective is of assigning certain tasks and workstation, certain tasks and resources to workstation, trying to minimize the total cycle time, also named the make span, the time to complete the assembling, and respecting some production constraints. Also, the aim of this study is to demonstrate the efficiency in terms of the scalability and flexibility of the proposed control strategy, because it is capable of act in case of real-time events like sudden failure, as we will see. So, first of all, we present the deep reinforcement learning framework, which is the technique developed in this study, where in reinforcement learning, we have two main characters, an agent and an environment, where an agent will interact through the action characterized by a policy, and since we are in a deep framework, our policy will be parameterized through a deep neural network, and interact with the environment, trying to find the optimal policy in a data-driven way. We will see more specifically. In particular, we have implemented the proximal policy optimization algorithm, where our agent is characterized by two factors. An actor model, which maps the observation to an action, observation from the environment, so it's our policies, and a critic, which approximate the state value function. So it evaluates the action taken from the actor in order to suggest to the actor how to improve itself to conduct better actions. Then, first of all, we go to model the environment, which is the assembly lines, and can be modeled through three sets: the sets of task, workstation, and resources, where each task is a vector characterized by three elements: start and finish time, and the durations. Then we find the workstation, which represent the unit of the assembly capable of processing the tasks, and the set of resources that can be consumable or tools like energy or operators. Also, as we said, we have to meet some production constraints that in our environment are, we have a mathematical formulation on these constraints. In this case, we present by words. And we have constraint on workstation like processing capabilities, and also workstation on tasks, like the fact that they cannot begin before certain resources have been assigned. Also, we have a precedence relation between tasks. In this study, we have considered finish to start relationship, and also the fact that each task can be processed in only one workstation at a time. Here we find the main element to model our environment, which is the state, which represents all the information and data useful to describe the each time step, the environment, but not all this information add benefit to the learning process. So we have implemented the observation, which is a vector scalar product of is a product of three vectors, one representative of the operative status of workstation, one for the tasks, and one for the completed task. As we can see in the example, we have 0 in the first, for example, in the first vector, we have 0 if our station is free, or 1 if our station is busy. And the same thing can be said for the operative status of tasks, 1 if it is processing, 0 otherwise. Then we have the action space, where in this case, different from many literature words, we have considered directly the assignment of tasks to workstation and not the dispatching rules. So our action space will be characterized by a vector where each element represents the ID number of a certain tasks, and the 0 which represents the null action, so no task assigned. Then we go to model our agent, where, as we said, is characterized by the actor and critic, and they are two deep neural networks. All the hyperparameters useful to implement the learning process, and also an experience reply memory, because the PPO algorithm is an on-policy, we have an on-policy learning. So the agent interacts with the environment collecting experiences that we will use in a second moment to update its policy. Here we can see more details the implemented algorithm, where first of all, the environment is initialized and the agent is queried to assign an action for each workstation. Then this list of action will be passed to respective workstation, and the environment goes forward by one step. The new assignment, the new task and resource are assigned, and the state will be updated to the next state. Also, in order to speed up the training, so in order to speed the learning of the agent in the environment, we have implemented an invalid action masking in order to avoid to take invalid action. We have done this simply taking the action probability from the actor network, and through an action mask which indicates which action is valid or not, we have created a masked categorical distribution, which is a categorical distribution when the values of invalid action are replaced with minus infinite, and then they will never be sampled. And in this way, we can speed up the training. Then, as we said, is an on-policy way, so we have to collect some the encountered trajectories, so the transition are stored in the experience memory. Why transition? Because as we said, our agent will select an action for each workstation. So we will have a different transition for each workstation. Then according to the update frequency, every hex episode, over a certain number of episodes, we have to update based on the experience collected our agent, in particular the models, the actor model parameters, so our policy and the parameters of the critic. First of all, we talk about the reward function, which is the main element of the reinforcement learning algorithm, because it is critical to shape the reward in a proper way in order to achieve our goal. And in this case, as we said, we have a different action for each workstation. So we have a different reward for each workstation, and each reward, the reward linked to the workstation is proportional to the duration of the task assigned to that workstation. And as we can see with this modeling, the agent is encouraged to assign tasks to operation unit. How our agent learn the optimal policy simply by maximizing the cumulative reward, which is nothing else that the reward, the cumulative reward from each workstation at each time step. Here we can see a graphic explanation of the proximal policy optimization algorithm that we have implemented, and the two objective and the actor loss function, which is the objective function through which the parameters of the actor model are updated. In particular, we have used the clip and surrogate objective that has the advantage to clipping the updates of the policy in order to avoid a recoverable path. Because, for example, if a certain action is more probable in a new policy, and the advantage to take that action in this state is positive, there is the possibility that to have a big updates on the policy and to fall in unrecoverable path. So we can find the optimal solution. Maybe we can find a suboptimal solution. And then we have the critic loss function, and as we said, is the critic approximate the state value function. So it's nothing else that a mean squared error between the predicted state value with the critic model and the rewards to go, which is a measure of taking a specific action in a specific state, and is represented by this equation. Where AT is the advantage, which represents the advantage of taking this action in this state and the state value of the current state, of the current observation. In theory, these T are subscript, but I don't know because now are not subscript. It will be R equal A subscript T plus BOO as a subscript T, where T stay for time steps. Then, in order to assess the performance of our real-time task control, we have performed 3 different tests, considering 3 different scenarios. But in these slides, only the results for one scenario have been reported. For the sake of simplicity, in our simulation, we have considered the workstation capable of carrying out any tasks. And in particular, we have coded the environment in Python. We have simulated a digital twin of our environment using Python. And for what concerns the PPO algorithm, we have used the TensorFlow libraries. So here we can see the simulation setup, like the relationship between task and resources, and also the parameter for the actor model and critic model, so the number of layers and nodes, and the hyperparameter useful for the learning process. In particular, we have parameters like batch size, which is the batches of experiences that we will use for update our model, or training frequency, which dictates the rate of the updating. Then we can see a first test conducted on 15 tasks, which will be scheduled on 3 workstations. On the table, there are the duration and precedence relation of the considered tasks. And on the figure, we can see on the top the score collected on each episode, and on the bottom the make span observed in each episode. And what we can say is that the learning is effective because the score curve increases until it stabilizes. And in particular, we find the optimal solution of 31 test steps. Then we have another test with 15 tasks with only 2 workstations in this case, and differently from the previous test, what we can say is that the optimal solution is found with less episodes. And this is obvious because with only 2 workstations, the possible solution are less. So the agent with less episodes try the optimal solution, find the optimal solution. Then we can see the task assignment, the Gantt chart of the 2 tests, the scheduling solution of our agent. And what we can see is that the workstation visit time is maximized. There is no time wasted in the scheduling of the task, as we can see. And also another test have been performed in order to assess the control strategy in case of real-time events. In this first case, we have simulated a failure on a task, in particular on a workstation, in particular on workstation 1, where we simulated that after 50 steps, the workstation 1 became unavailable. So as we can observe, the task 8, which is running, is interrupted prematurely, and then will be rescheduled on the other 2 workstations, and the scheduling will continue with only 2 workstations. And what we have to say here is that there isn't the necessity of retraining our agent to continue the scheduling. And this is the main difference with classic control, which is model-based. Then we have another second test, where in this case we have considered a task failure, and also, whenever the task 8 is taken into account, we simulate a failure on task 8 after 3 time steps. And we can see that also in this case, the agent is capable of continuing the scheduling without the necessity of being retraining. And the task 8 has been rescheduled in a second moment. Also, we have made a comparison with the mixed integer programming result in order to assess the optimality of the solutions, in order to verify if the solution that we have found with our control strategy are the optimal one. So as we can observe from the table, we have found the optimal solution. And the main difference with a mixed integer programming, which is at the basis of classic controller like model predictive control, the execution time is immediate. And this is an important characteristic in case where the dimension of the problem became larger, because this execution time can increase. So in this study, we have proposed a single agent reinforcement learning framework, which generates promising results in terms of the minimization of the make span, and also in terms of efficiency, because as we have seen, it is scalable, it is flexible, and allow, let me say, more degree of freedom, because as we said in more literature works, the action space is characterized simply by the dispatching rules. Instead, in this work, we consider directly the assign in each step, the agent consider directly the assignment of tasks to workstation. In future works, it is possible to extend this current study to more complete problems. So in a multi-objective approach, or for example, adding additional features on the state or on the action space or on the production constraints. And also it is possible to adopt this approach on a multi-agent with a multi-agent approach, simply assigning a different agent for each workstation, and implementing a parallel and coordinated training. And also, it's important to conduct tests on larger scenarios. That during these studies, we have done tests on larger scenarios, and we have obtained encouraging results on this sense. But since there is a bigger sensitivity to hyperparameter of this algorithm, and the hyperparameters used in this word are selected by hand with the trial and error, it is not simple to obtain the optimal solution. So in this sense, it's important to conduct a test on larger scenarios. Thank you.
Any questions? Not, I have one. So there are many heuristics for solving this
Yes.
problem in scaling. So you compared with MIT and you have shown that, of course, this method is faster than one that obtained the exact solution. Actually, two questions. Have you compared also with standard heuristics, which may give you a fast response on both
No.
in less time? And second, what happens if, because you have tasks which have to be executed with some deadline.
Yes.
So there may be no solution for your scheduling, or it's any case in which your system.
No,
requires-
there may be no solution because they meet the production constraints, and we have also start
So
deadline.
what happens that-
We give a solution that, but not respect all the constraints in this sense. Which is not the optimal solution in this sense.
Okay. Professor?
What do you say about the simulator? Exactly doing.
Una slide?
Yeah, in one of the slides.
Ok, la riprendo se vuole. Ok. I don't know which slide.
Relation.
Ok.
We understand these are
Ah, the other tests. The other test. Back.
we implemented that approximately
Yes.
and you are testing data. You also implemented the pipeline.
Yes. The environment will simulate the dynamic of the assembly, like assigning new tasks and resourcing, and also going one step ahead on the tasks that are running. So decreasing the total time to complete the task, decreasing the workstation busy times, all the dynamics linked with the assembly lines.
So as time goes by.
When you say that.
Yes, because once the agent is trained in each time step, he knows which is the best action to perform, which is the best assignment. So once the trained is now on the training, we have not simulated potential failure because in this way, and since also we have the invalid action masking, in this way, there isn't the necessity of train also in case of failures because for which is the environment is simulated, and also the algorithm using this invalid action masking, there isn't the necessity. Because as we can observe by the graph, there isn't no time wasted also after the failures and during the failures. There isn't a stop of workstation or solution, or for example, wait action are assigned. Ever tasks are assigned, and in order to achieve our goal, if we maximize the busy time of workstation, you will reach a near optimal solution. Okay.
Okay. Thank you again. So, the next presentation will be by Flavio Clarizia. Okay, is on the merging of bearing rigid formations. And supervisor is Professor Andrea Cristofaro, who's not here, but is listening to us through the Zoom. So he's remotely connected.
Yeah.
You can see.
Okay.
Devi spostare per vedere lì. Mhm. Metterlo sull'altro schermo. E come faccio? Non lo so perché. Poi va venire sull'altro schermo. Io la valutazione. Io la valutazione. No, non sta avviando la roba. Ah, ok, ok. Sta avviando. Questo se lo devo spostare giusto. Ok.
Okay. Good afternoon. My name is Fabio Garizia, and I'm presenting my master thesis about developing a strategy for managing very rigid formations. So rigidity theory has been applied for several years in different fields, like construction, mechanics, and biology. But with the advent of multi-robot system, as found is a natural application, for example, information control. So the problem of merging rigid formations, which is the topic of this thesis, has been widely studied for the case of distance rigid networks, but so far never for the case of band rigid networks. So in this topic, the objective is to develop a methodology in order to merge two band rigid formations. In the literature, rigidity theory divides into two fields: distance rigidity, which studies a formation that had to maintain distance constraints between the agent that formed this formation. And in this case, robots, for example, had to rely on sensors in order to measure the distance between them and the neighbors. For example, having on board GPS sensors in order to localize their position and share it with the other agents, so compute the distance. Instead, band rigidity studies how the robots maintains bearing constraints between each other. And in this case, robots can use, for example, camera sensors, which are innately bearing sensors. So cameras, so band rigidity has the advantage that it can, in many applications, it can be used, for example, in GPS denied environments. Instead, distance rigidity, since it relies on GPS, cannot work in this case. For example, in case of the space applications. So we can see first some applications about rigidity in general robotics. For example, we have formation control or formation keeping, in which agents have to form desired formations, which has need to have desired distances or desired bearings, and they have to keep it while moving in the space. Then there is rigidity maintenance, in which, for example, some connection due to obstacle or sensor malfunctions can be lost. And in this case, rigidity maintenance operates in such a way that rigidity property is maintained. Then there is the rigidity component identification, in which the desired formation, we have a larger formation, and we have to identify sub-rigid components in this formation. Since with better rigidity, there is the very only formation control, in which the formation is formed only relying on bearing information. Then there is a splitting of formation, which a large rigid formation is split into two sub-rigid formations, and the merging, which is the topic of this thesis, in which two or more rigid formation have to form a larger rigid formation. So a short overview of rigidity theory, we can say that a formation in general, a multi-robot system, can be described like with a graph, in which each node of the graph is a robot, and each edge is the connection, communication channel between these robots. And when we talk about rigidity, we speak about frameworks. And a framework is a graph together with a mapping, which map each vertex of the formation. So each robot with a position, with a number in the real space, for example, a position. And a framework is said to be rigid if the distance rigid if for continuous motions of the nodes, the distances distance constraints within the nodes doesn't change. So, for example, in the left we see a flexible framework, while in the right we see a rigid framework. And in order to have rigidity, a minimal number of connections has to be maintained. So in general, it is 2 multiplied by the number of vertices minus 3. This is minimal rigidity. It's important to see, in order to develop the theory, how rigid frameworks are constructed. And this is done by using the Hilbert construction, which is a sequence of iterative steps, namely vertex addition and edge splitting, which, if done, build a rigid framework. Vertex addition, starting from 2 nodes connected by an edge, add a vertex to the network by connecting it to 2 already existing vertices of the networks with 2 edges. Instead, edge splitting removes an edge in the network which already exists, and add a vertex by connecting it with 2 edges to the nodes that were previously connected by the removed edge. And a graph constructed in this way is called a Laman graph. We can see now, introduce now Baron rigidity, since it's the topic of the thesis. And given a set of fixed bearings between the agents, we had that a framework is very rigid if, given these fixed bearings, the geometric pattern of the network is maintained. So as before, we see in the left is not a very rigid framework. It's the geometry of the network changes. In the right is very rigid. And again, a minimal number of connections has to be maintained, which is again 2 times the number of vertices minus 3. So an important theorem that has been used in order to develop the theory is the following: that if a graph is Laman, so built using the Hilbert construction, then is generically very rigid in arbitrary dimension. So if it's very rigid in 2 dimensions, it's also very rigid in 3 dimensions, in 4 dimensions, and so on. And so this implies that 2 times the number of vertices minus 3 edges is sufficient in order to guarantee Baron rigidity in any arbitrary dimension of the Euclidean space. And this is true only in the case of Baron rigidity and not the distance rigidity, because for distance rigidity, if we increase the dimension of the Euclidean space, the distance constraint increases. While for distance rigidity, this doesn't happen. So if we increase the dimension of the space, the Baron constraints remain fixed, remain the same. And so this applies well. And so we can develop the novelty of this thesis. So we can first introduce the merging problem. We say that given 2 very rigid graphs, namely G1 and G2, then the merging of these 2 very rigid graphs consists in finding the new set of edges to be introduced in order to connect this graph in order to form a larger very rigid formation. And to do so, in this thesis has been developed an optimal, find an optimal number of edges to be introduced. So the minimum number of edges that have to be introduced in order to have the merging. And it has been found that in any dimension, in any arbitrary dimension, only 3 edges are sufficient in order to merge the formations. And also, in order to minimize the number of robots involved in the merging process, an optimal node selection has been developed, and has been found that only 2 vertices, so 2 robots per formation, have to be involved in the merging process. So the strategy, the outline of the strategy is the following. First of all, we have G1 and G2, which are the 2 formations. And the idea is to grow G1 with the vertices of G2. So to do so, in order to do this optimally, so minimizing the number of edges to be introduced, implicit and explicit edges have been exploited, which are edges that may already exist or may not, maybe implicitly exist. And we apply then the Amber reconstruction to add the node of G2 to G1. And then we define an optimal vertex selection in order to minimize the number of agents involved in the merging process. So the strategy is the following. First of all, let's consider two very rigid formations called G1 and G2. So we say that the idea is to extend G1 with the vertex of G2. So to do so, we pick a random vertex of G2, and we call it NU. And we want to add it by means of vertex addition. You can either choose vertex addition or splitting because both have the same number of edges. So for simplicity, we choose vertex addition. The first step is to verify that the two formations have any node in common, and that the first stage is never true because they are two different formations. And so we connect the NU by means of two edges to G1. And so we grow G1 with this vertex of G2. So we have G1 prime, an information G1 prime. So in this case, now we have to verify if this formation is very rigid. So we verify if the number of connection is 2 times the total number of vertices of the formation minus 3. And we see that this is not true because one edge is missing. So we have to again continue with the strategy, and we pick a different vertex of G2, and we want again to add it this time to G1 prime. This time we verify that the two formations have G2 and G1 prime. G2 and G1 prime have any vertex in common. This time we have NU. So it means that having a node in common, an explicit or implicit edge between the two formations exists. So in this case, for example, if we choose vertex 8, the explicit edge 8,7 is already present. So this means that we can use this edge and add just one edge in the process. And so adding this edge, we find that we have 2 times the number of vertices minus 3 edges. And so the overall formation is very rigid. Now, since we want to minimize the total number of agents involved in the process, we can pick as a vertex of G1, so G1 or G1 prime, we can pick the G1 prime, the previous vertices that we choose in the previous step. So for example, in this case, we could pick vertex 2 or vertex 1. So this, I pick vertex 2. We can see a simulation, and we can do it with a very rigid formation of unicycle. And since you can consider the kinematic models is good enough for the purpose. So we do a dynamic feedback linearization, and we apply the control for double integrators. And we see two very rigid formation of unicycle moving in the Euclidean space. We can do this in 2 dimensions if the number of edges is the same also in 3-dimensional in higher dimensions. And we see that the merging happens at t equals 40 seconds. We can see also a short video for clarity. Okay, and now we can draw our conclusion and talk about feature research. We have seen that rigidity has many applications in robotics, and in order to have rigidity, a minimum number of connections have to be established. We see that the merging problem of rigid formations involves finding the minimum set of edges to be introduced in order to merge the formation, and that for very rigidity, only 3 edges are sufficient. Moreover, choosing optimally the agents, only 2 edges per formations can be used. A possible future research, which would be interesting, is to do the merging of very rigid formation in different spaces, and not only the Euclidean space, for example, in SE2 or SE3. And thank you.
Any questions for while you were doing this simulation at the end, you show a controller for the unicycles with some error. So the control law. What does this represent? the error between one formation and the other formation? I don't understand.
No, it's the control for each agent.
Yes, so why you wait 40 seconds to do the merging? What happens in between?
They are two separate formations.
But why they are connected at 40 seconds? Connect at 20 seconds or?
Yeah, you just do this for purpose of simulation. So.
Okay.
Okay. Okay, they are no, they are. We need to have 3 edges. I mean, it's necessary. Yes, I mean. Okay.
Maybe more. Depending on the dimension.
No, they can't be more because they're always 3 in any dimensions. I mean, for the
It's necessary. If it's not increasing the dimensions.
For sure, it will be necessary. Okay.
I mean, it's I think it's necessary and sufficient. Yeah. Because we need to have 2. Yes, it has sufficient. Yes. Well,
I think it's sufficient. Thank you again.
Thank you.
So we move to the next presentation
excuse me.
by Martina Domini. She will present her thesis on anomaly detection with LSTM autoencoder, which we will learn what they are, using reaction wheel model data. The advisor was Professor Francesco De Nittis.
Good evening. My name is Martina Donnini, and today I'm going to show the work of thesis that I have developed in the past few months at Thales Alenia Space. This work is a propedeutic activity to the invitation to tender as a fiorire. So the objective of my thesis is to perform anomaly detection in a reaction wheel by using synthetic data. And after that, I had to reduce the size of the model since onboard computers of a satellite have a limited memory capacity. So a reaction wheel is basically a control attitude device, which is used to rotate the satellite around its center of mass. And first, going into the machine learning part, what I did is to implement the reaction wheel model on Python in order to generate this data. So after that, I had to identify which data to take into account in order to perform anomaly detection. So in literature, I found that there are some possible faults that can occur in a reaction wheel. And in particular, these faults can be due to voltage unbalance, current unbalance, and temperature unbalance. And so I analyzed the commanded voltage, the temperature of the wheel, and the output torque, which is proportional to the current, and also the output velocity. These data are actually multivariate time series. This will mean that each variable will depend not only in its own past values, but also by the other variables. So another aspect is that I will not have any label on my data. And so I will use an unsupervised learning technique method. In particular, I use autoencoders which are neural network models whose structure is formed by an encoder which compress the data and a decoder which will decompress the data. So in general, autoencoders are trained to reconstruct the input data, and the difference between the output and the input is called a reconstruction error. In order to perform anomaly detection, the model is trained with nominal values, so that when in the test space we add some new values that are, for example, faults on anomalies or new data that the model has never seen, when the autoencoders try to reconstruct the data, it will generate a higher reconstruction error. And so, by setting a threshold, if this reconstruction error is greater than this threshold, there will be detected an anomaly. So, since we are dealing with time series, we will have a sequence prediction problem. And so, in order to handle this kind of problem, we will model the encoder and the decoder part with long short-term memory networks. So our final model will be called the long short-term memory autoencoder. Now we are going to see the various cases that I studied in order to understand if my model actually works. So the first case is the satellite operating in nominal mode without any anomaly on the dataset. Second case is the satellite operating in nominal mode, computing a maneuver profile, always without any anomaly. And the last case is the satellite operating in nominal mode with some anomalies. So here it is, the results of the first case. And as we can see in figure A, this is the whole data set with no anomalies. And this is the basic wheel signal for maintaining a fixed altitude of the satellite. What we wanted to show here is that if we don't have any anomalies, the anomaly detection algorithm will not detect any anomaly. And so it is, as we can see in figure B. In this second case, a trapezoidal type profile was reproduced to perform a z-axis maneuvering. And what I wanted to show here is that if I train my model with this kind of data, with this trapezoidal profile, I will expect that if in my test data I will have a similar signal that corresponds to a maneuver, it will not be detected as anomalous. And so it is, as we can see in figure B. Now, for the last case, I had two cases. In the first one, as we can see in figure A, an external failure has occurred, and this will cause an increment in voltage in the voltage time series that will consequently generate an increment of velocity, temperature, and torque. For the second case, instead, as we can see in figure B, I decided to implement a friction failure. And this failure will generate an increment of temperature, and as a consequence, will generate also an increment of velocity and torque. So, based on these two types of failure, I can classify two different kinds of faults: an external one and an internal one, internal to the wheel, I mean. So I analyzed both cases in my thesis, but here I will show only the internal failure. And so, as we can see in figure A, we can see the whole data set with some anomalies. And in figure B, instead, we can see that the algorithm has detected the anomalies. So we can see them in red. Now, after anomaly detection part, I will have to optimize my model, since, as I already said, the onboard computer satellites have limited memory capacity. And so it is important to reduce as much as possible the model that I used, so it can be run on board. The three techniques that I use are pruning, quantization, and collaborative optimization. In particular, the first technique that I analyzed is pruning, which is a technique that it is used to induce sparsity in weights by removing some parameters. In particular, removing a parameter will mean to setting it equal to 0. And one can think to prune the model with different percentage of sparsity. And we can see here also in this figure how the weights of the model changes with different percentage. In figure A, in fact, the 80% of the model has the weights equal to 0. I also give some evaluation of the model. So we are going to see that the mean absolute error will increase with an increase of the sparsity in the model, and it has to be as close as possible to 0. And also the R2 score, which has to be as close as possible to 1, will decrease. And so a trade-off between reduction and performances is to choose a model sparsity with 50%. Now we can see that the algorithm is still working even after pruning the model with 50% sparsity. In fact, in figure A, the algorithm is still detecting anomalies. And in figure B, we can see how the weights of the model changes by pruning the model with 50% sparsity. Second technique that I used is a quantization technique. And this technique will reduce the dimensions of the model by decreasing the precisions of the weights. So for example, if a neural network uses a 32-bit floating point representation, this technique will convert the precisions into 8-bit integer representation. And so by doing this, a lot of space in terms of memory has been saved. In figure B, we can see that the algorithm still works and still detects the anomalies. Lastly, we can see the last technique that I used to optimize the model, which is a collaborative optimization, which is nothing else than applying pruning with 50% sparsity and then applying quantization. Also here, we can see that the model is detecting, the algorithm is detecting anomalies and still works even after a compression. Another compression. So at the end, we can evaluate also how the matrix changes with these different techniques. And so we can see that the mean absolute error slightly increase, and also the R2 score slightly decrease. And in terms of reduction and performances, we can choose the collaborative optimization as the best that we can achieve in this kind of simulations. Now, to conclude, we can say that I created a representative hardware flight of reaction wheel, and I generated synthetic data to perform anomaly detection with a long short-term memory of encoder. Moreover, as I already said, I reduced the size and the computational complexity of the model so that the algorithm can be implemented on board. And as I already said, this work was a propedeutic activity to invitation to tender as a fiorire. Thank you for the attention.
Any question for Martina Domini?
Yes. Mm-hmm. Which case? Oh, yes, I have this here. Yes. Okay. It's okay.
So io non sono una versione proprio su example, for example, anomaly, or are you compare the reality and approach to the expectancy? And also reasons for which reality can is more suitable.
No, I applied directly this model. I did not compare to other models.
I have also a question. This is the friction anomaly, no?
Yes.
So this times on the x-axis, you have this anomaly occurring around 20,000 seconds, whatever.
Yes, about
So
yes.
why the scales are different? What does it mean that 750 something happens?
Okay, maybe here I wrong I have the graphic that is wrong, but it will be 0. It would have been 0 to 100, 1,000. I just see that I wrong.
So my question is, you know, that
Okay.
question is, are you processing? I mean, you're getting this type of result by processing the whole data set, or as soon as this anomaly occurs, then the detector is able to. So you have to process the whole batch of time series?
Yes, in the training phase, I give to the model the training data set with no anomalies. Then in the test phase, I give the one that is in figure B, the data set that is in figure B, with which has some anomalies. I don't know if answer the question.
No, in fact, is that are you doing detection online or
Offline.
offline? So you have to have the
Yeah.
full setup. Okay. Other question?
Yes. Okay, what I did is to model two different networks. One for the univariate voltage time series, and one for the multivariate remaining terms, so velocity, temperature, and torque. So if the voltage the voltage univariate time series is faulty, this will mean that an external failure is occurred. While if I will have the univariate time series non-faulty, this will mean that it is an internal failure. Obviously, I did not study on specific classification technique to distinguish if the anomaly comes from temperature or velocity or torque.
Okay. So thank you again.
Thank you.
Next is Pasquale Forgione. His thesis is on model predictive control of autonomous robots with discrete time control barrier function for obstacle avoidance. And the supervisor is again Andrea Cristoforo.
Hi, I'm the student Pasquale Forgione, and today I will present you my work thesis on the model predictive control for autonomous robot with discrete time control barrier function for obstacle avoidance. During this presentation, we're going to do a brief introduction about the autonomous navigation, then we will see the aim of the project, and then we will focus on the implementation setup, in particular on the unicycle model, the dynamic feedback linearization, and then proposed nonlinear model predictive control, discrete control barrier function. At the end, the simulation results and the conclusion. Autonomous navigation is the ability of a machine, a robot, or a vehicle to safely and accurately navigate from one point to another without the human assistance. It became increasingly important in the last decades thanks to the rise of the demand for autonomous robots, drones, and vehicles. Autonomous navigation allows the robots to travel safely and reliably in an environment where the human cannot or do not want to be, such as the underwater, the space, or hazard areas. Moreover, the autonomous navigation allows the autonomous vehicle to travel with high speed while avoiding obstacles and other vehicles to reduce the risks of collision. There are some existing works that tries to combine the advantages of the model predictive control and control barrier function to this aim. And inspired by this previous work, a nonlinear model predictive control for the safety critical task with discrete time control barrier function enforcing the safety critical constraints is proposed. The main idea of the safety critical system is to create systems that are intrinsically safe and that minimize control and reduce the impact of the hazard. Developing this system is more or less similar to the development of other kind of system. However, it is crucial for this system that the final product performs exactly as planned in order to prove their reliability and feasibility. The control barrier function are usually defined as margin function. Based on this definition, we can define the safety set and the boundary set respectively as S and delta S. Now, we can say that a system is safe with respect to a set S if such set is forward invariant. From the definition of forward invariance says that for a dynamical system, a forward invariant set has a set that has solution evolving within the set. Now, based on this, we can give the definition of barrier function and in particular of discrete barrier function. This barrier guarantees that the changing in the value over time is always greater than or equal to minus gamma h. In this case, gamma is between 0 and 1, which ensures that the margin is always positive and also that adjusts the variance along the trajectory. Now, combining this with the model predictive control, the feasible set becomes the intersection between the reachable set and the safety set, that is the area colored in yellow. So this means that with a good choice of gamma, we can confine the system movements even if for the obstacle avoidance, even if the robot is far away from the obstacles. And in particular, if the value of gamma is 0, the system converges slowly to the safety set, but can quickly become infeasible. On the other hand, if the value of gamma is closer to 1, the problem is feasible in a large domain, but can quickly become unsafe. And this is what I want to overcome in my project. For the implementation setup, I consider a model of the unicycle, and then I convert this nonlinear model into an equivalent linear one by the dynamic feedback linearization. And then I apply the nonlinear model predictive control, discrete control barrier function, performing various simulations to ensure the effectiveness of the proposed controller. The model of the unicycle can be expressed by the following equation, in which we have two inputs that are the linear velocity and angular velocity, respectively v and omega. Then I define the output x and y of my systems, and then I compute the relative degree and the coupling matrix that in this case is singular. To avoid these singularities, I need to add an integrator on the linear velocity input in the following way. Doing this, I can apply the dynamic feedback linearization, obtaining the following dynamics compensator. So these lead to a system that is the following that we are going to consider also for the simulation, and based on this, we can perform a change of coordinates. This change of coordinates leads to a fully linearized system that is described by two simple double decoupled integrators. The proposed control logics solves the following finite time optimal control problem. We can notice we have one horizon length n that is designed for the dynamics constraints, input constraints, stage cost, while another horizon length n CBF that is less than or equal to n is designed for the control barrier function in order to reduce the computational complexity. In particular, in this formulation, we have P and Q that are the terminal cost and running cost, which minimize the error between the output of the robot and the reference signal. And in addition, we have the relaxation cost psi, that is the penalty function for the relaxation variable, which minimize the difference difference between the control barrier function and the nominal decay rate by keeping omega near to 1. Of course, initial condition, dynamics constraints, input constraints, and state constraints are imposed on the optimization, and in particular, the dynamic model considered for the prediction is the easier state space model of the two decoupled double integrators, and moreover, constraints to avoid the singularity on the Xi introduced by the dynamic feedback linearization is added into the optimization. To overcome the problem expressed previously on the control barrier function, from the fixed value 1 minus gamma, the decay rate is relaxed into an optimization variable that is omega times 1 minus gamma, and these lead us to a control to improve both feasibility and safety at the same time. So for our purpose, the design of the control barrier function is the distance between the robot position and obstacle position. For what concerns the simulation results, I consider a circular path that the robot must follow, and I analyze the case in which I know the behaviors of the obstacles, and the case in which I only know the position and behaviors of the obstacles samples per samples. I also study the performance of the controller at different obstacle velocity, both for known and unknown dynamics case. The first that I want to show is the circular path. The system parameters and optimization parameters for the known dynamics case are the following one. And in the environment, we found 2 statics obstacles and 2 dynamics obstacles. How we can see the robot track its trajectory, and when encounter the obstacle, it finds the faster way to avoid it. Thanks to the prediction and knowledge of the obstacle movements, it found the faster way to avoid the obstacle and to return to track its trajectory as soon as possible. The same thing happens for the second dynamics obstacle and the other 2 statics obstacles. In the video on the left, we can see in red the reference signal and in blue the output signal. What changes in the unknown dynamics case is essentially the prediction horizon of the control barrier function that now is set to 1 instead of 8. But what this means? This means that now we cannot do prediction about the future movement or location of the obstacles. In this case, the robot, when avoiding the obstacles, starts to move in the same direction of the obstacle, but doing nothing. Only when the robot starts to descend, the robot has the possibility to recover and continue its path. Regarding instead the second dynamics obstacle and the other 2 statics obstacles, there are no remarkable differences with respect to the previous case. Again, on the left, we can see the error and the reference signal and the output. During the course of the work, one important aspect that I had to deal with was the obstacle velocity. I noticed that when the obstacle has too high speed compared to the robot is not able to find a feasible solution. So for this reason, various simulations had performed. The system parameters and optimization parameters for this simulation are the following one, and in particular, the prediction horizon for the known dynamics case is equal to 5, while for the unknown dynamics case is equal to 2. The first simulation, the robot is faster than the obstacle. The robot moves with a velocity of 1 meters per second, while the obstacle is with a velocity of 0.5 meters per second. How we can see for both the cases, there are no problem in avoid the obstacles, and since there are no differences between the 2 cases, I decided to show you just one simulation. In the second case, the robot and the obstacle has the same velocity, 1 meters per second. And even in this case, for both the controller, there are no problem in avoiding the obstacles. And even in this case, there are no remarkable differences between the 2 controllers. In the third case, instead, the obstacle is faster than the robot. In this case, the latter travels with a velocity of 1 meters per second, while the obstacle with a velocity of 2 meters per second. In this case, in the known dynamics case, as we can see, the robot is still able to avoid the obstacle, even if the distance between the two is very small. Instead, in the unknown dynamics case, the robot is not able to find a feasible solution. In order to do a deeper analysis and to find the velocity limits even for the known dynamics case, I performed several simulations, and increasing the velocity of the obstacle to 3 meters per second, the controller is no longer able to find a feasible solution, even in this, but at least with these settings. I also compared my controller with some existing controllers, and in particular with the model predictive control distance constraints, which use the distance from the obstacle as a constraint, and an MPC in which the distance is weighted in the cost function. For both these controllers, we can see that the problem became infeasible after a few samples. This means that these controllers are not able to handle this kind of problem, while my approach can do it without any problem, as can be seen. So during this presentation, I presented a nonlinear model predictive control for safety critical task, where the discrete time control barrier function enforces the safety critical constraint. We have seen also that in the optimization, by relaxing the decay rate of the control barrier function, this leads to improve both feasibility and safety at the same time for both one-step and multi-step optimization. And also I verified the properties of the proposed control design with a unicycle for obstacle avoidance, first on a circular path, and then in a more complex scenario where the obstacles travels with a high speed with respect to the robot. Thank you for listening.
Very interesting, yes. Any question? Oh, I have one, please. So you enforce a constraint which is on the state of the dynamic feedback in the right system.
Yes.
This controller has singularity when the robot stops. So
Yes.
this constraint avoids the robot to stop.
Yes.
So what happens when turning on face? That
Okay, I can show these what happens when the robot stops in a place and about the singularity. Let me just check the slide in the background. Okay, for example, in this experiment, no, it's not the correct one. Try to find the slide by hand. Okay, for example, in this situation, we can see at the end of the video, there is a little bit slow. Okay. In the last frame is that when the robot stops and to avoid starts to go around the center of the mass in order to not stop the velocity. And so these create the fact that the robot is still able to continue to work.
So it never stops.
It never stops. Yes. Yes. If it is stopped in a place, they continue to work and to, because the velocity never reaches zero.
And the other thing is that you have this gamma parameter, which at some point you write gamma of k, which means that this gamma.
Yes, yes.
So what is the rule of chaining? There's some dynamics that.
Yes, this is what I have explained in the first slide. When with this value of gamma is the key point of the control barrier function, because by choosing gamma, we can increase or decrease the safety or the feasibility of the set. In particular, in the slide 3. Okay, here.
No, but what I meant is that decide a priori how to change this, or this is changing because of the condition?
The gamma is chosen at the beginning, so it's a parameter that is chosen first. But thanks to the introduction of omega, so this slack variable into the optimization, these lead to change at each steps the value of this decay rate. So while before this formulation, the decay rate was constant from the start to the end of the optimization. In this case, is not true because change every time.
So it's changed a lot.
Yes, it's changed a lot.
Okay, thanks.
But really, there is also the possibility to go in backward. Yes. No, I have not handled this part because I'm just concentrating on the fact that the robot it must avoid the dynamic obstacle and the static obstacles. And I handle just of course the singularity introduced by the dynamic feedback linearization, but it may be that the robot find the best solution to travel in backwards situation and avoid the obstacle in a backward situation. It's a little bit strange, but yes.
So either you go forward or you go backward. You have to decide. And we go forward now. Thank you very much.
Thank you.
So next presentation is by Valerio Giuffre. He's presenting a thesis on patient-robot physical interaction control for robot-delivered hyperthermia treatments. And the advisor is Professor Maria Elena Venditelli.
So good afternoon, I'm Valerio Giuffre, and I work with my advisor, Professor Maria Venditelli, to the thesis on patient-robot physical interaction control for robot-delivered hyperthermia treatments. In the medical procedures frequently use robots to assist in the treatment, assuring several benefits, such as an increasement of the precision in the treatment, better comfort for the patient, or a facilitation to dispense the treatment for the medical staff. In this thesis, the medical procedure treated is the hyperthermia. The hyperthermia is a medical treatment that uses it to kill cancer cells or make them more sensitive to other cancer treatments, for example, chemotherapy or radiation therapy. The aim is to rise the temperature of tumor tissue to a range of 40–45 Celsius degrees for about 1 hour, in order to induce an inhibition of tumor cell repair mechanism, which try to recover the damage caused by the cancer treatment. In addition, increase the blood flow and cell membrane permeability, resulting in an improvement of radiation therapy and the delivery of chemo agent in the tumor site. Up to now, the radio frequency applicator or microwave applicator, the antenna, is positioned manually in a location indicated by the clinician with a passive mechanical arm without any automatic control or imaging guidance. So there are some limitations, such as the decreasing of accuracy caused by the manual positioning of the antenna, or the impossibility to reproduce the same position of the antenna in subsequent sessions, or the absence of an automatic tracking of the antenna pose during inevitable movement of the patient, both macroscopic movement and smaller movement related to, for example, the breathing. So the robot project that has as a partner the Medlogix SRL, the University of Rome La Sapienza, and the Amsterdam University Medical Centers aims to eliminate this limitation using a manipulator to move and hold the antenna to the desired pose, fully in collaboration with the human operator, monitoring the error and the interaction force with a digital twin virtual. For imaging guidance, localization and tracking algorithms are used to match the reconstructed tumor location from the computer tomography or magnetic resonance images. The robot has an interaction control that will be continuously active in order to detect and handle unwanted contacts with the environment and with the patient. So the objective of the thesis is to validate and compare impedance and admittance control schemes in order to have a safe and easy antenna placement, guarantee at the same time high accuracy in the execution of the treatment with a compliant adaptation to human movements. Overall, the desired accuracy can be reached only closing temperature feedback for irradiate volume. But this is still a work in progress, and the robot is the first necessary step to reach the accuracy for the treatment. So to do this, several interaction controllers have been tested in different conditions of increasing realism. First of all, on MATLAB, with the same ideal model used both for simulation control design, then on Coppelia Sim, with the ideal model used for control design, and on server side, a model simulated in Coppelia Sim, and then with a real robot finally. The robot used is the Panda robot by Franca Emica. It's a manipulator with 7 degrees of freedom, all revolute joints, and a prototype of the antenna is attached on its end effector. Starting from the dynamic model in joint space, we have M as the inertia matrix, C the correlated centrifugal matrix, G the gravity term, and F the generalized force applied on the end effector. So, computing the transformation from joint space to Cartesian space and making the feedback linearization, we have the dynamic impedance model as a mass spring damper system, where MD is the desired inertia matrix, KD the damping gain, and KP the stiffness gain. Imposing the desired inertia matrix equal to Cartesian matrix, the contact force is simplified. So if the control is compliant, a measure of contact force is not needed. The impedance control generates as output a force in reaction to a motion in input. Vice versa, the admittance generates a reference motion in reaction to an external force acting on the system. So both impedance and admittance control have the same dynamic model, but with different implementation. In fact, a measure of contact force is necessary to implement this controller. For comparison purposes, I tested 5 controls: the PD control with gravity cancellation, three feedback linearization control, one with Cartesian damping term, the second with joint damping term, and the third with Cartesian damping term and joint damping in null space, and then a kinematic PID control. The results are shown in this table. The only controller that is able to maintain a high level of accuracy both in simulation and with the real robot is the PD with the gravity cancellation. The only negative aspect of the PD is that in simulation there is the presence of self-motion, but in real robot it does not appear. So even if even the PD not have the redundancy handling, there are not internal joint motion because the action of the friction and the joint friction, not modeled and not managed in the control law, acts as a brake on the entire chain of the robot. So in the treatment, the controller used are described by this equation. Talking about the treatment, the entire robot motion is divided into three phases: the manual guidance, the adjustment, and the interaction phase. In manual guidance, the operator can move manually the robot. The manipulator in this phase has a passive behavior. In fact, the controller compensates the gravity term in order to prevent the robot to fall on the patient or to collapse on itself. The aim of this phase is to position the antenna near the tumor site. After the manual guidance, the adjustment phase and the interaction phase. Both are the same desired pose with a difference of 15 centimeters along z-axis with respect to the base frame for safety reason. In fact, the delivery of the robot, this division is guarantee a sustained speed approach in the first phase, in adjustment phase, guarantee at the same time safety behavior because the antenna is positioned higher respect the patient, and so avoiding possible collision with the patient. And finally, in the interaction phase, the robot can move the antenna with low gain and a soft approach on the tumor site. During the treatment, sorry. Okay. Yeah. During the treatment, the patient could move the antenna placed on it unintentionally, making voluntary movement or simply movement related to the breathing. So the controller must support this contact force in a compliant way, and it must be able to return to the desired pose. In this video, we can see how the robot yielding behavior when an interaction occurs. So the graphs show how the tracking error return near to zero after a contact force, after an interaction occurs. So in conclusion, among the interaction control laws tested, the PD with gravity cancellation result to be the best control choice for the treatment because it has a good trade-off between high level of accuracy for execution of the task and safety of the interaction. It is simple to implement with few parameters to tune, and it has no self-motion due to joint friction. Thanks for your attention.
Did you, when you're doing the simulation part in Coppelia
Yes.
or MATLAB, did you model also friction in that case, or?
No, without friction.
So this is, you mentioned probably that, the reason why you don't have self-motion in the real robot, why you would have it in the.
Yes. And yes, in the real robot, the only in the real robot we don't have the self motion, and estimate the friction. I have seen that the level of the friction is not negligible for this case. Thanks.
So next is Riccardo Izzo. He's presenting a thesis on traffic control with model predictive control and deep reinforcement learning, a comparison. And the supervisor is Professor Francesco Liberano.
Good evening, my name is Riccardo Izzo, and today I'll talk about model predictive control and deep reinforcement learning for traffic signal control. Traffic congestion is a worldwide problem. In fact, the European Union, together with 192 countries all over the world, signed the Paris Agreement in order to reduce CO2 emissions. Particular traffic congestion may be a dangerous problem since it leads to air pollution, disease, and large waste of time and money for the time spent in queues. A possible solution may be of expanding the transportation capacity, but this will lead to many costs and the building of new routes. In fact, the solution we propose is to improve the traffic signal controllers already existing. In particular, today we have periodic sequences of light in the traffic lights and phases with fixed duration. So our suggestion is to choose lights adaptively instead, and to consider also a variable phase duration. Our objective, my objective of the thesis is therefore to improve the intersection of the performance by selecting the optimal traffic lights sequence adaptively. Particular to different approaches are proposed. So a first model-based controller, namely a model predictive control, for which I will describe the waiting time modeling of each vehicle at the intersection, the introduction of variable constraints, and also the choice of an objective function. Secondly, also a model-free deep reinforcement learning algorithm is proposed. In particular, a network is first trained in order to let the agent learn how to behave, and afterwards tested on a new scenario. Model predictive control is an optimal control technique in which the calculated control actions minimizes a cost function for a constrained dynamical system over a finite horizon. In particular, the main idea behind this control strategy is based on an online optimization. So at each time step, optimization problem will be solved. In particular, according to the process model, future outputs are predicted over an horizon. Then a set of future control signal is computed in order to follow as close as possible the reference. And finally, just the first control signal is performed and sent to the model. In this framework, the main feature is the introduction of a model in which we actually model the waiting time of each vehicle at the intersection. This actually ensures a better control strategy and enables also the optimization of a new key performance indicator. The main thing in this work is the fact that thanks to the introduction of additional auxiliary variables, I was able to keep the mathematical formulation linear, leading therefore to a mixed integer linear programming problem. In particular, as a dynamics, we consider the waiting time of each model, and in particular, we model the waiting time in such a way that it grows as long as the vehicle pulse stays at the junction, and it is set to 0 instead when it leaves the junction. In particular, a several set of constraints are introduced as a single state constraints in order to the traffic light to light on just one light at a time. Moreover, also a light transition order constraint is introduced in order to force the traffic light to have the right order of transition. A yellow time minimum duration is also set up in order that after every green light configuration, also a yellow time light is turned on for safety reasons. Conflict avoidance is also mandatory for this formulation in order to avoid conflicting lanes and collision between vehicles. Finally, a set of constraints in order to model waiting time is introduced in order to update the queue with the arriving and leaving vehicles. Finally, the cost function was chosen in order to minimize the sum of the square vehicles in order to ensure stability in the intersection and also fairness. As a model-free approach, instead, I propose a deep reinforcement learning algorithm in which, unlike the MPC controller, there's no need of a process model, and it is also actually suitable for high-dimensional state space problem. In particular, the agent learns how to behave just by interacting with the environment through a trial and error approach and without having any prior information. In particular, based on the action performed by the agent, the environment provides a state and a reward to the neural network. The state is the information about the environment provided to the agent at each time step, while the reward instead is used by the agent in order to understand the consequences of the latest action taken in the last state. This information are then provided as input to a neural network, which will be trained and will provide as output the new action to perform at the environment. And the proposed the proposed state is a raw vector providing information on each line about, in particular, the number of vehicles halting at the traffic light, the total waiting time of each lane, and in particular, the average arrival rate of each lane. This element is fundamental in order to the agent in order to have a look-ahead control. The actions instead are chosen by the agent within a dictionary of actions. In particular, I consider three green light configurations where will be then intervaled between a yellow light. In fact, as we can see in the state machine, the three light configurations 1, 2, and 3 can just or repeat themselves or pass on another green light configuration by going through a yellow light one. As a reward function, instead, the community waiting time was used. And in particular, we can see that if the community waiting time at time t is larger than the previous one, then the agent should be penalized since he has taken a bad action. Otherwise, if the community waiting time is less than one calculated at previous time step, this means that intersection performance are improving, and therefore the agent should be favored. All the simulations are applied to a real intersection of Rome in Italy, and in particular, a 3-hour scenario is considered. In the first hour, we have a low traffic intensity, having a few long queues. Second hour with medium traffic intensity conditions, and finally, third hour with very high traffic intensity condition. In particular, we generated the vehicle arrival as a Poisson distribution, and therefore considering each vehicle, the generation of each vehicle as an independent event. Moreover, from an inspectional view, we also recovered an arrival rate for each lane and for each traffic condition. The multi-predictive control framework was implemented in Julia programming language, using also an online solver with a third-party solver for the optimization problem, which is globally optimization. The deep reinforcement learning algorithm instead was implemented in Python, thanks to the several libraries as TensorFlow and TensorFlow. And finally, both softwares were then interfaced with a real traffic simulator, namely Sumo, in order to provide real traffic data. Finally, both results are validated
by comparing both controllers with the current fixed periodic strategy. The model predictive control simulations were carried out using a prediction horizon of n equal to 60 and a sampling time of 1 second. In particular, we can see that this controller is able to manage the traffic in all the 3 scenarios. In low and medium traffic intensity, this is outperforming the baseline controller. In high traffic intensity, instead, we see that while the current strategy is actually diverging, making the system unstable, MPC is able to manage this problem. Simulations were made, as we said, for both key performance indicator in terms of Q length and also waiting time, in which we can see that, again, the model predictive control shows real excellent performance with respect to the baseline one. As we said in the beginning, for what concerns the model-free strategy, we first trained a neural network, first trained an agent in a training phase. And in particular, we can see how during all the training phase, the cumulative negative reward and therefore the commodity waiting time is actually maximized, providing a stable and optimal policy. At the same time, also several key performance indicators as the average number of vehicles halting, the average waiting time are drastically minimized. And at the same time, as motivation of the stasis, also the cumulative CO2 emissions are actually reduced. The train model was then tested on in the exactly same scenario of the baseline and of the MPC, providing excellent performance. In particular, again, in both Q length and waiting time terms, we can see that the train model outperforms the baseline controller in all the traffic intensity. The main side of this work is actually the fact that this train model was able to be applied and it was suitable for each traffic intensity. And therefore, just one train model was enough to control the intersection. This was the simulation, a video simulation in which the real traffic intersection was simulated using the 3 suggested controls. And it showed that actually in the first hour of first hour, so low traffic intensity, the DQN and MPC were able to manage the situation. Same thing for medium traffic intensity. And it showed also that in high traffic intensity, while the baseline was becoming, making the system unstable, DQN and MPC were able to manage instead the situation. Finally, yeah, actually it should, it should, but it was assumed, it did actually. Okay. Next time. Finally, a comparison between the 2 techniques also was proposed. And we saw that despite model predictive control was able to allow us to introduce constraints on each variable of the problem, and also allows to introduce an objective function which allows the engineer to maximize or minimize any variables of the problem. However, this technique requires a process model, which is not always easy to implement due to nonlinearities. Moreover, this control technique is not suitable for high-dimensional state problems for complex process models. And finally, since it solves optimization problem at each time step in an online way, it is not actually really suitable for real-time computation. Finally, instead, the DeepQ network, despite the choose the correct state space information to provide at the agent and the designing of the reward function, we saw that no model was required since it learns how to behave thanks to the interaction with the environment. It was suitable for high-dimensional state problem, and finally, also provided excellent performance in real-time implementations. In conclusion, so we have proposed 2 different control approaches in order to enhance the intersection performance. A proposed model predictive control actually showed great improvements with respect to the current control strategy. The model-free, instead, deep reinforcement learning algorithm actually outperformed the baseline controller, showing effectiveness for any traffic intensity condition. At the end, both the control strategy were simulated in a real traffic simulator, providing, again, excellent performance. And actually, further improvements can be done by a better modeling of the departure rate and the arrival rate of the vehicles. Also, newer techniques are also able to improve our results. And finally, this problem can be also extended to a multi-agent environment, also extending the problem not on a single intersection, but to an extended road network. Thank you.
Yes.
Of course. Yes. Yeah. Yeah, actually, as I said, this this problem can be extended to a larger road network, also thanks to multi-agent environment. The main fact was that actually the train model was able to deal with different traffic intensity. So we just have one train model that was able to manage all the traffic intensity. For what? Yes, for what concerns the road network, actually, yes, another intersection should be the agent should be informed about the new intersection. Yeah. Yes. Exactly. The model predictive control describes accurately the dynamics of the queues, so it actually is actually more scalable. But you know, it actually needs a process model, which is not easy to implement. Exactly. Exactly. These are the drawbacks. Yeah. Yeah, but predictive control was not actually suitable for real-time computation because, you know, at each time step should solve an optimization problem. So it was not actually suitable, really suitable for in real time. That's it.
Very nice. Perfect. Yeah.
Exactly. Yes, I did. Exactly. Of course, yeah, we simulated the pre-inspectional view. We saw like the duration of each traffic light, and we simulated the arrival rate of each vehicle and also the duration of each phase of the baseline controller. And we simulated it in Sumo. With in the exactly same scenario, we also simulated the model predictive control and the DQN, and which actually outperformed the baseline. So it was a realistic simulation. Yes, exactly. Yeah, through an inspectional view, actually.
So standing at which junction?
And it's a secret.
It's a secret.
No, it's depicted here, but I started from work or my professor Liberati, so
Somewhere in Rome.
exactly.
Okay. Okay. Thank you very much. Thank you. So, next presentation is by Seper Tavanei Tabrizi. And he will be talking about transfer learning for optimal character recognition of metal engravings in the oil industry. And the supervisor is Professor Pietrabissa, who could not be here.
Yeah, but okay. Mine is not
okay.
so I have to change it. Otherwise, I cannot see. Okay. There we go. Okay. Hey, hello everyone. My name is Sefer Tawanai, and today we're going to talk about my thesis, which is about the transfer learning for optimal recognition optimal character recognition of metal engraving in the oil industry, which was a project for the Technic company here in Rome. So the table of content would be the first introduction of the thesis, and then we're going to define our problem. The methodology will come after, and the result, and also the conclusion. So about the introduction, in every industry, detecting and recognition of the metal engraving character has a huge and significant role in documentation of the company, and also the updating the data sets that they have, because each single one of them, they carry so much information with themselves. So for so many years, this process has been done manually by the operators or the employee in the companies, and it's a tedious, error-prone, and also time-consuming job, and also it's a cost for the company to have as much as human resource to do that, because they have a lot of metal pipe or other elements in the company, and also consequently it make the efficiency very low. So with the development of the computer vision and also machine learning, finally companies decided to change the manual area into the automatic ones. And because they convinced that the automation of the company would ensure the profitability of the company, and also it reduced the cost and the time for them. So this process has been done with the two options here. The first one is an ad hoc camera, which they are expensive and not so many companies want to do that. The other option would be the software-based solution, which we are working on it because it's a cost-effective, and also it's really easy to use for the employee. So in this thesis, we're going to describe the optimal character recognition, or OCR, and combining with the transfer learning. So if we want to define our problem, it's about, since we were working in an actual environment, detecting and recognizing the characters in the oil company had so many challenges for us. There are so many of them here. Like the first one is, since we are working with the metal aluminum, the brightness and the reflective material would make detection and the recognition part difficult for us. Also, the angle that each photos are taken is so important, because this process just mostly work in some desired angle. There are a variety of the background and the color. Since we are working in a metal engraved one, it means that they have the same color, the characters and the background have the same color. So it's also, since we have the multiple background, it's another problem. And the metal corrosion can cause some or the total part of the character destroyed. So we cannot understand what was the character there, and it's difficult for the network to assume that character. So the methodology that we presented for the company was combining not the OCR but the deep OCR with the transfer learning for the recognizing these characters. So when we are working with the deep, we kind of assure that the deep learning would help us to tackle any challenges in the computer vision. And here, with the deep learning-based OCR, we could identify the labels of the objects and the region proposal better. And also, since it's a deep neural network, it's using the neural network such as YOLO, RCNN, or any other ones. And also, deep OCR are beneficial for us to detecting the text that has a limited temporal information to rely on, such as the signboards or maybe the plates of the vehicles. And also, compared to other OCR methods, deep learning-based methods, they are much more robust to localize the characters regardless of their deformation or the fonts and any other problems. And also they can gather all the characters together so it comes as a word or as a line or whatever we are looking for. Also, on the other hand, transfer learning means that we can use and we can use the information from one neural network and transfer all the knowledge to our target neural network without having so much annotated data and images. And also it helps us to strengthen the accuracy of the system, aligned with reduce the computational cost of the rebuilding another neural network from the scratch. So OCR basically means that we want to convert virtually any image containing the written text, such as the type 1 or the written one, into the machine readable text data. But we should notice that the OCR method is kind of sensitive to some situations, such as the paint, corrosion, pollution, or maybe the lighting, and etc. And almost they are perfect for the PDFs or any well-printed text with knowing fonts. So because of that, OCR has 4 steps, so we can tackle these issues each by one of them. So the first one is pre-processing, detection, recognition, and sometimes we can use also the post-processing. It depends on our data sets and what we are working on. So the pre-processing is the vital and the crucial steps for advancing and enhancing the rate of the success for our project. Since we are working in the situation that, as I mentioned before, the character and the background, they have the same color. So the background and working to make sure that there are difference between the character and the background, so the OCR can detect them, and the recognizing part can understand what was the word is so crucial for us. So the pre-processing steps here, since we received so many images from the company from different dimension and different sizes, so we wanted to use the resizing to make sure that we are focusing on the area that exactly where is the image are, where is the text are. And also with the help of the color correction, we could reduce the noises, and also we could help to recognize the edges of each character. And also there are another application we could use here was the Kalahi, and it's a contrast limited adaptive histogram equalization, which is a family of the adaptive histogram equalization that basically take care of the over amplification of the contrast. And it makes sure that by enhancing the contrast, we could see the text in the image from the foggy or from the noisy images. So detection part, the detection part is the next part, which is the process of locating the object which we are looking for in an image. These objects could be anything like the text, signboards, or any other things. So the text detection and the segmentation are often known as a text localization because they are working side by side in the pipeline methods. And with the help of the localization, we can convert any text contained in the image to the words, line, or the characters that we are looking for. There are two families of the detections family. There are two families of the text detection. The one is the traditional one, and the other one is the deep learning methods. So the character region awareness for text detection is a deep learning neural network method that gives us 2 scores for the character region and the affinity region. And with the help of these two scores, we can make sure where the characters are or the words are, and also it helps us to increase the accuracy. And also it's so good for using the bounding box when we have the situation of the long or the curvy or maybe rotated and deformed situation, that we have both all of them here in the oil refining company. So the recognition part is the part that comes after when we have the bounding box, and we want to understand what is the character is, and we want to classify that one. So here we use the pre-trained model because we wanted to make sure it increased the accuracy and also it's reliable for the company to use that method. The recognition part, we have so many options to use, but the most famous one using the CNN-based methods such as the convolutional neural network or the recurrent neural network or the combination of them. So here we trained this model was trained on the since 90K dataset, which is a dataset of the 9 million images based on the 90,000 English word, which they have so many color or they have the different background, noisy or any other problems. And also it has 7 convolutional neural network with the 2 fully connected layers. And also all these sequence came as a pipeline method, which all the sequence automatically goes each one after another one, and which is the processing, detection, recognition. And maybe after that, we can also update the data set of the company automatically. So the transfer learning. The transfer learning is, as we mentioned before, it's a method that we can use to transfer the knowledge of one to another one. And there are comes in a different methods, like it depends on the data set that we have. If we have a data set from 100 to 100K, so we can use a different methods here. And also there are 3 approaches of the transfer learning, the pre-trained model, fine-tuning, and the feature extraction. But in this particular thesis, and it was a traineeship, we use the pre-trained model for the recognition part and also fine-tuning that one. So the fine-tuning, it means that it makes the pre-trained models domain applicable to our data sets by keeping the certain parameters fixed and also retrain the other ones that we want to retrain. And mostly it's the top some top layers of the neural network. So here we had fine-tuned the recognizer on our data sets, because we should mention that our data set, it wasn't only about the character recognition, the character engraved on the metal. Also, it was split to the handwritten ones, and the handwritten ones about 35, and the metal engraving ones was about 10. So basically together it was less than 50. So we could use, by using the fine-tuning on our data set, and also fine-tuning the recognizer on the MNIST datasets, which is the 60,000 images of the 0 to 9 digits, because we had a problem of the recognizer to recognize the numbers mostly, not the characters. We could improve the numbers and letters there. And here are some results. So we have some results about the metal engraved characters first. They came as the first one. They could understand and they could recognize as multiple characters here, and also there are some very destroyed characters on the metal engraving, and there are some example of the handwritten ones that they could understand. But as we said before, there were some problem about the understanding mostly the numbers here. So as a conclusion, the method that we offered to the company was working on the both data sets that we have, the handwritten ones and also the metal engraved characters, and also the detection part to detect these metal engraved characters was almost as we expected, but also we have the problem with the recognition part, since we have a lack of data sets, so consequently we have a less accuracy. But since it's an ongoing project for another coworker here, so we're gonna, if we have more data sets and labeled one and annotated one, we can definitely make sure that these methods will help the company to tackle their challenges and to be usable for the employee to use them as a software or maybe any other option that they want to use. And thank you for your attention.
Any questions? Original time. So when you're talking about few data, so how
Yes.
many images did you get of the different types?
We had 35 images of the handwritten ones, and we have almost 10 images of the metal engraved, and also 2 or 3 videos that we could use on. So it was a few for us, because at least we need to have 100 or 200 images for using to be the best, to have the best accuracy that we want to use.
Why did the company provide?
Oh, the company is providing, but they have some bureaucracy with themselves, so so they are updating the data sets of the images, and it's an ongoing project, so we can work on it afterwards. Thank you.
Thank you. So next presentation will be by Luca Tirelli. Safe and scalable deep multi-agent reinforcement learning for assembly line scale. And the supervisor is Professor David Isco.
Hello, my name is Luca Tirelli, and today I'm going to present safe and scalable deep reinforcement learning for assembly line scheduling. I'm dealing with the generalized assembly line balancing problem that is a specific type of NP-hard combinatorial optimization problem that involves the mathematical definition of a factory and use it to deduce the optimal planning of the activities. This kind of strict project management is needed especially in complex safety-driven aerospace projects in which even small delays due to poor planning may lead to high unwanted costs. And this is why I've developed this work in the context of the Cézanne project to improve the competitiveness of the European companies in the market of satellite launchers. And by having a look to this table, we can have an idea of the magnitude of the costs involved in this kind of industries, where a single kilogram of extra payload may cost up to $1 million. In literature, this kind of problem was first addressed by classical methodologies and then by problem-specific heuristics like genetic algorithms. But the main issues in this kind of approach is that the lack of framework robustness, in the sense that if some unexpected event affects the initially planned scheduling, then there is a need of recomputing a new scheduling from scratch, leading to further delays. In order to avoid this, I've developed an HAB-E-based method that makes use of reinforcement learning, providing framework robustness to the agent thanks to the reusability property. This was one of the main motivation that guided my work, and within the main innovation, we have the development of an action masking technique to enforce safe state trajectories, and the use of this action masking in the decentralized context to develop a sequential logic that enforce safe cooperative behavior within the agents. I formulated the problem both as an optimal control problem and as a reinforcement learning problem, but due to shortage of time, I will only expose the reinforcement learning formulation in this presentation. These are the main parameters involved in the definition of the factory, and they are important to understand the main dimensions involved. We have, for example, the first representing some dimensions like the number of tasks to be done, the number of workstations, the different type of resources, but we have other parameters that represent some numerical values for the constraints involved in the problem. In particular, we have, for example, a time precedence, a specific fixed number of initial resources, or we have different capacities for the buffers. And all of these parameters are used to initialize the reinforcement learning problem and enforce the constraints. The two main components of the reinforcement learning problem are actually the states and the actions, and I define the states to be a concatenation of several states. the occupancy state that is proper of the workstation and represent actually the current amount of tasks being handled, the duration states that actually represent some residual durations of the task being processed, and the resources state representing the amount of resources stored in the workstation buffer during time. The type of actions, the actions are of two types, the tasks and resources action, and are directly linked within each other's. They are represented through Boolean matrices and Boolean tensor, where a positive value represents actually the assignment of tasks to specific workstation and assignment of resources to specific workstation buffers. The main problem in the reinforcement learning formulation was actually embedding the constraint into the process. In fact, while in classical optimization, this was straightforward, in the reinforcement learning context required the definition of a feedback signal from the state. This was done by augmenting the environment, providing it with the capability of computing an action mask that is actually a state-dependent differentiable function. And this mask is provided to the deep centralized agent that use it to compute the next feasible action to be applied on the environment. And what we can see in this slide is actually the control scheme for the centralized problem. This is just an example of how the dynamics of the factory works, in particular for an example in which we have 3 workstations and 5 tasks. We have the action that is taken at time 0 that, for example, is a valid action that assigns the first and third task to the first workstation and the 5th task to the third one. And once the assignment has been performed, actually the duration of the task starts decreasing during the time. And another state that actually affect the process is the level of the workstation inventories that vary during the the evolution of the dynamics of the factory. The 2 main algorithms developed and proposed and actually modified to solve the problem were a DQN algorithm, in particular a more advanced version that makes use of double dueling learning, and the PPO algorithm. I reported their pseudocode here to highlight where the main modifications were being performed. In particular, they were performed in the action selection step, in which we provided the mask to the trained agent that could in this way enforce sampling of feasible actions. And we have also some modifications in the learning step of these 2 algorithms to propagate on masked values. These are the main results for the centralized problem formulation. In particular, the problem was solved in the context of optimal control, and the optimal solution was K star equal 9, that is represented in this plot by this flat black line below. And both the algorithm managed to converge to the optimal solution K star equal 9. What we see, the green lines are actually an average of the ending times achieved during training computed on a moving window around the current values. And the shaded area represents just 1 standard deviation from that value. The reward function used for the 2 algorithms is the same, and it's proportional to the minimum ending time achieved. The action masking mechanism is highlighted in this slide. In particular, the centralized learner is provided with 1 state and outputs, depending on the algorithm, the probabilities or the Q values. And these values are then masked thanks to on the basis of the value of the mask to output a filtered probabilities. Thanks to recent work in literature, we are now sure that the policy the use of a state-dependent differentiable function ensure the satisfaction of the assumption in the policy gradient theorem. Thus, the derivative of the policy with respect to the parameters is guaranteed to exist. And in order to prove the efficiency of the action masking, I've trained 2 PPO different agents with and without action masking. And actually what we see in the plot in the bottom left, it's the rewards achieved during the training process. And clearly the PPO provided with action masking achieve higher reward during the training, while the red one doesn't exhibit convergence, but that is not restrictive. We provided the not unmasked PPO with a negative reward at each episode in order to produce this simulation. The main limitation in this work is in the action space explosion. In fact, we have that the dimension of the action space is directly dependent on the number of tasks to be processed and solved. And we managed to achieve, I managed to achieve to reduce the cardinality dependence of the dimension of the action space from the number of tasks from an exponential to a polynomial dependence by decentralizing the problem. And in this plot, we can see how the action space dimensions vary while increasing number of tasks. For this kind of scenario, we expect to have really high number of tasks, thus the decentralization strategy must be applied to ensure the correct working of the algorithm. And in particular, the decentralized formulation were performed by switching from one centralized agent that to multiple agents, one for each workstation. Actually, the agents share the observation, but they have different action space and masks. And we can define the goal of the multi-agent system to be a cooperative goal, to finish all the tasks as fast as possible. And this is the control scheme for the multi-agent problem, in which there is this new block that is action sequential feasibility check. The main difference with respect to the centralized context is that while in the centralized context was enough to provide an agent with action masking to achieve a nice behavior, instead in the multi-agent context, there might happen conflict and within the agents. In fact, for example, two different agents may choose to assign the same task, creating conflict in their decisions. And in order to solve this problem, I've defined this sequential control loop in which the first agent is provided with a real factory state and output a valid feasible action. This action is then provided to a fictitious environment that compute an action mask, a new fictitious action mask and state to be provided to the next agents in the loop. And this is continued until we exit from the loop with a feasible concatenated action, but this action is resulting from several agents' decisions. And here on the top right, we see the difference between the centralized action thought as a Boolean matrix and the decentralized action that can be thought just as a row of it. These are the two main pseudocode developed by me for the multi-agent PPO training loop. In particular, on the right, we have the multi-agent PPO training loop that makes use of action masking. And the algorithm one execution is called before applying the action on the environment. Actually, this first algorithm that I presented in the previous slide is rendering the next agents in the loop being capable of see what the first one or the previous one did, allowing them to compute actions that can be concatenated with the first agent's choices. And these are the final results for the multi-agent system. In the DQN and PPO cases, we see that in the plot on the top, we have the rewards achieved during the training, again computed on a moving window around the current values. The shaded area represent one standard deviations, and the losses on top for the DQN and PPO algorithm are reported. The PPO algorithm exhibit a better behavior, having 50% the parameters of the DQN algorithm and showing a convergence in less episodes. Thanks to this, we were able to achieve this Gantt chart for this simple toy example with 5 tasks and 2 workstations. From this, this actually is the final outcome of the work that represents the scheduling of the activities to be done that respect all the constraints imposed by the factory. We can see, for example, that the task 1 and task 2 respect the time precedence that exists between them. And actually, this Gantt chart, this code was tested with a bigger scenario up to 50 tasks. Also, the trained agent was then initialized, the environment was then initialized in a random state, and the trained agent was evaluated on the randomly initialized scenario and managed to achieve optimal solution the 95% of the times, while the other 5% were suboptimal solutions. And this let us select the PPO multi-agent as the best algorithm for this case. And this is the end of my presentation. Thank you very much.
Okay, thank you.
Thank you very much.
So, Michele Viscione is presenting meta-learning by optimizing condition parameters of differential simulators. And the supervisor is Professor Luca Io.
Hi, I'm Michele Viscione, and I will discuss now the thesis, which I carry out for the past 10 months in collaboration with Bielefeld University. And yes. So I will provide only a discussion of the most basic form of the novel proposed meta-learning framework. And this form will be focused on a specific case study, which is the simplest one. And yes. Okay, so let's start with a toy example. Okay, suppose that we have videos of pendulum with different length L and friction B. We refer to this underlying condition, these parameters as condition parameters, and we will use the theta symbol to refer to them. Therefore, we want to train an artificial neural network to guess which of these frames are related to a pendulum with close to zero velocity. So for each of the frames, the artificial neural network will provide a probability value which addresses the likelihood of the frame to be of a small velocity one. We will then measure the task error by means of a loss function, as it is usual, and for example, the mean square error. And we can also plot this loss landscape of the artificial neural network over a range of condition parameters. This is the same plot, but in 2 dimensions, so with a color map. Okay, normally we sample from a given this training distribution, and since we do not have any prior about this specific task, we will usually perform a uniform sample. So we will sample from a uniform distribution, and but as we can see, there are zones of the loss landscape which are pretty relevant, and in fact, certain tasks are harder for the learner, and we need a way to generalize and provide further training on these zones. In fact, we would like something more like this, where a lot more data points, training data points, are provided for the yellow zones, which corresponds to the Hanagher value of the loss. But this is usually not possible because this requires prior knowledge, and both in forms of knowing which task is harder, and also this is random because depending on the training, the model can generalize better on some zones or others. So to tackle this problem, we need to define a solution which acts adaptively first, and then this solution has to be tunable with respect to the task, because it happens usually that when we overstress the training on harder zones, we might end up with a so-called catastrophic interference, where the artificial neural networks focus too much on how to succeed in our harder tasks and forgets how to deal with the easier one. So to do so, let's say that we want to train a model, namely the learner, to perform some generic task, which is measured through the task loss L. This model takes as an input the synthetic data given by this differentiable simulator. Differentiable simulators are a class of data-driven techniques which goal is to obtain a surrogate model of a given dynamical system. So this model emulate other complex systems, which are maybe difficult to construct by physical and mathematical methods. And in particular, this one is context-based. So it means that given a first portion of the state trajectories, it forecasts the continuation of the system dynamics. In particular, the context, so the first portion of the trajectories, are generated through a synthetic data generator, which can be any numerical system, numerical integration scheme like Runge-Kutta-4 or other differentiable simulators. Or alternatively, this can be provided by means of data collection like real measurements or any other collection of real data. And yes, so a first part of the differentiable simulator will take this context and decode some sort of internal representation for the condition parameters. This is not usually, these do not encode usually only the condition parameters theta, but also many other features. And it is used by the differentiable simulator to understand which are the characteristics underneath the system depicted in the context. Therefore, the differentiable simulator will take both this condition, the latent condition parameters and the context, and will forecast the continuation of the dynamics. Moreover, it can take also other inputs like control inputs and so on. It's quite general. And yes, so this is an example of differentiable simulator I built, which forecasts the dynamics of a pendulum. So the part before the dashed blue vertical line are the context, while the part after is the forecasting of the differentiable simulator for both the angular position and the angular velocity. So this architecture is quite general and applicable in realistic scenarios, since we can train it with from real measurement data. It is also used in literature, so we can apply our method to out-of-the-box differentiable simulators. We can also, this method do not require strictly the presence of a SDG, so we can use we can really train on realistic data. And we perform also system identification, because by mixing machine learning techniques and the output of the DS encoder, we can we can retrieve the information about the condition parameters underneath the pendulum, for example, or the system. So we want to find a way to systematically provide harder instances for the training instances for the learner model. And since if the whole pipeline is differentiable, we can try to get a gradient-based technique as an example. In this way, we can take the state trajectories of the pendulum and transform them into a video differentiably. This has been done in the thesis work. And so now that the whole pipeline is differentiable, what can we do? We can perform a classic gradient ascent procedure and find the next loss increasing hidden parameters. And yes, but this usually doesn't work, because since the hidden representation of these parameters is higher dimensional, and since we name the P theta the submanifold of the real physical parameters, which are embedded in this theta, in the theta space, theta star space. So the elements of this P submanifold are the elements corresponding to real pendulums, for instance. And outside of this theta of the P theta star submanifold, we have non-physical pendulums, maybe pendulum that shrinks, pendulum that works strangely. And so if we seek to raise the loss value through gradient ascent, we will immediately go out of distribution, because the learner, for instance, has never seen any data from outside this training distribution. So from this submanifold, so the loss will be definitely higher. So to solve this, we would like to optimize directly on P theta. But to do so, we need a way to parameterize these real theta star elements. So to sum up, our problems are the following. We need to find loss increasing condition parameters by optimizing directly on P theta star. And once we found the new values, we need a way to compute the new grade, the new context related to the system with this condition parameter. In fact, if we change the condition parameters underneath the context, although the context changes slightly, we can see that the continuation of the dynamics changes relevantly. So a key, an important element that we want to that we will use is the compressor model. The compressor model is a neural network that takes as an input the hidden condition parameters and reconstruct the original condition parameters, theta r, which hopefully is close to the real theta. And this is done by means of a K subnetwork. While with a R subnetwork, with a R subnetwork, we will try to project back this theta r embedding into the P theta manifold. So the Ascend learning is a meta learning framework where we inject the compressor within the DS encoder and the DS predictor in such a way that we can compute directly the gradients within P theta star. Therefore, once we have the new theta r, we can generate a new context by means of a synthetic data generator as an instance. And so in this way, we find systematically new and harder tasks. But if we want to keep the Ascend learning independent from the use of synthetic data generator, because usually it is not general to rely on a synthetic data generator, we can compute, we can train another network, which namely the shifter, which takes the previous context and the displacement in a theta space and generate the new context related to the new found theta parameters. So this kind of network is based on a recent result, which is the Noether networks, which are neural networks inspired by the Noether first theorem. And yes. So to sum up, we sample first a context and we train on this context. Then we try to find the new best, the new local increasing task condition parameters. And when by means of a SDG or by shifting the previous context, we find a new context. Then we train on this context. And finally, we repeat the steps 3 to 5 for n times. And finally, we go back to the step 1. As we can see, this is an example for this is always the toy example we mentioned before. And in the figure below, we have the blue plot represents the ground truth for the starting task, while the green plot represents the ground truth for the last task. Although the difference is slight, we can see that the prediction for the original task, which is the orange one, is quite on point, while the prediction for the last task is definitely not so good. So we found efficiently a way to compromise, let's say, the training. And sometimes the difference between the starting and the lasting task are quite relevant, as in this case where we start with 3 inversion of motion and we end up with 4 inversion of motion. So more complex task. And as a baseline, this is the loss landscape we saw before. And for the learner trained with a classic approach. And this is the delta loss, which is the loss under the classic approach minus the loss under the Ascend learning. So the higher the better, the higher the more the more the improvement of the Ascend learning. And both are performed under the same number of training instances. This is important. And this shows that the Ascend learning improves greatly specifically into the harder zones. Also, you can see that there are pieces where the the normal training performs better, but because these are the easier zones. So of course, if the number of sample of training instances is the same, will be always the case. So take as an instance these are the first as the starting training distribution. So from this we want to see what is the distribution after the assent learning. As you can see now, it is the yellow zone is more populated because for each orange with original training instance, we found the new harder one. So we are training both on the orange and on the red. And this is done by one-step assent learning. But if we do two-step assent learning, we see that even more elements can be found inside the harder zone. And by fine-tuning this method, we can improve greatly and the results of the method. So other applications, in a nutshell, we have first a topology optimization. I simulated a nearly landscape where the balls falls driven by gravity, and simply the theta parameters in this case encodes the topology of the landscape, and we can see that we can try to optimize the landscape in such a way that to convey all the balls in specific spots. And this works with compressor injection, while with straight plastic optimization, this doesn't work. So we are not able to convey the balls efficiently in specific spots. And while another application is the robust network orchestrator, where we have a network of devices, each with its own transmission range and with its own battery. And each battery is emulated by means of a Dynaformer, which is a state-of-the-art differentiable simulator, which emulates the battery dynamics of a lithium battery. And yes, this shows that this method works also with out-of-the-shelf differentiable simulators. And yes, in this case, we are trying to activate the nodes of the network in such a way to connect to pre-specified nodes. The plot below, the figure below, represents for as an instance the shortest path between the 8 from node 8, which is the lower one, to node 6, and this is performed with the Dijkstra algorithm. While the learner one is the one above, and this is also robust with the discharge of node 0. So in this case, even if node 0 discharges, we are good, let's say. And another application, which is a work in progress, is to given a different reinforcement learning based controller for the Karp-Pohl inversion pendulum, we want to improve the range of controllable condition parameters, which in this case represent the pendulum mass and the length. And we want to be able to control the pendulum for a broader range of possible pendulums. And this is for now is a work in progress. And yes, other advancements are application to reinforcement learning, as discussed before, and extension to stochastic setup, especially also in the reinforcement learning scenarios. This is quite relevant. And unlabeled dataset. So when we have dataset of real measurements without labels, and also we might want to use this to perform physics extrapolation of neural networks. Thank you.
Any questions? Which is involved for the training of the other code. So if I understand, I'm sure that if I have a code that works more or less like a transformation matrix or a transformation tool for the one that stays, So the changes the development and the map in order to follow less the guided of your classification path. Sorry, of your learning path.
Yes, kind of, because the compressor, it is used to let's say parameterize this submanifold. So what we do is to we take elements of the theta of the hidden representation of the condition parameters, and we project them. So this works quite as a narrow projector, if I have to connect this to other projects. And yes, it takes this, but it doesn't alter the overall representation of the differentiable simulator, because the output of the decoder, let's say of the compressor, it should be on the same line of the input. So we try to, the theta hat start should be similar to theta start. We are trying just to compress all the elements into the forcefully compress all the elements into the parameter space. But this is the simpler version, because there is also another general version where we have also pass-through variables which encodes time variables and time features and so on. And in that case, it is quite more complicated and can be related more to this case. Yes. Yes. No, this is not the case, because there is also an approach where we force the compressor to be inside the to project directly the theta star into the we use this as a pure projector. But in this case, the projector can never be zero, because we start every time directly within the theta space, because we are optimizing within the p theta. So let's say we are not finding a new theta star value, and then we are projecting them back. We start from the first one, which is likely physical, which is likely inside this submanifold, and then we move inside this manifold. So we never find solution which are zero half. Well, this is a problem for other approaches where that was the first approach we had for this work.
Okay. Good. Thank you, John. So this is the before last presentation. Actually, the last of the control engineering master is Dario Zurlo. He's presenting his work on collision detection and contact point estimation using virtual joint torque sensing applied to a couple.
Okay, so good evening, everyone. I'm Dario Zurlo. Under the supervision of Professor Alessandro De Luca and Merlin Morlock, I carried out my thesis at Neurorobotics on sensorless collision detection and contact point estimation applied to cobots. The aim of this thesis is to develop a reliable algorithm to detect a possible collision between the robots and an obstacle, isolate the collision, identify the external torque and, if possible, the external force, and react in a suitable way in response to a collision, using only the motor torques, the joint position, and the joint velocities. First of all, I'm going to present the two collision detection algorithms in the blue box, then the collision reaction in the orange box, and in the end, the estimation of the contact point using the modified contact particle filter in the green box. The contribution of this thesis is twofold. The first contribution is a combination and a validation of two existing sensorless collision detection methods. The second one is an adaptation of the contact particle filter for the contact point estimation to reduce the computation time. Why collision detection? Because cobots can be operated in the vicinity of human operators and in general not in structural environments, so not in closed cell, and therefore they can collide at any time, harming a person or breaking an object. And we want to prevent this from happening. Why contact point estimation? Because collision detection can be also used for physical human-robot interaction. And why sensorless? Mainly because sensors are expensive, in particular force sensor and joint torque sensors. The first method is the one based on the energy of the system. The idea is to compute the residual energy that is given by the difference between the measured energy and the energy that we inject into the system since we are controlling it. Of course, on the real system, in addition to the motor torque, we have to consider also the torque due to friction. The idea is that collision will change the energy level of the system from which we can detect the collision. On the right side are shown the result in simulation in which I commanded the robot with a random motion. I applied an external force, and when I apply this force, on the energy residual is present a peak from which I can easily detect the collision. In all the other cases, the residual is equal to 0. The second method is the one based on the generalized momentum. It is possible to prove that if the gain KO tends to infinity, the residual approximate the external torque. On the right side are shown the result in simulation. In this case, I applied an external force on the third link, and in fact, the first three components of the residual are different from 0. All the others are equal to 0. From which we can detect the collision, but also we can infer which link collided. Also, we can see that the residual approximate quite well the external torque shown in the third plot. We have seen in simulation that if there are no collision, the residual are always equal to 0. Unfortunately, on the real case, since we have a mismatch between the dynamical model and the real system, the residual are in general different from 0, even if there are no collision. For this reason, we can combine the two methods to get a more robust algorithm. And a possible way to combine the two methods is to detect a collision if both methods return true. Otherwise, we just ignore that one of the residual is different from 0. For the same reason, we must define some threshold to avoid false positives, so that when a residual exceeds the threshold, the method returns true. A possible way to define this threshold is as a sum of a constant threshold, a threshold that depends from the joint velocities, and a filtered version of the residual. Using this last contribution, we assume that the collision excites the residual at high frequency, which is reasonable for many unintentional collision. Once the collision is successfully detected, the robot should react in a proper way. In this thesis, I test 3 different reaction strategies. The simplest one, stop the robot, and the behavior of the external force. In this case, when the obstacle is constrained against a fixed object, is shown by the curve with the dashed line, which present a problem because the force in the second region is different from 0. And to solve this problem, we can compensate the gravity or compensate the gravity and add an additional torque that push the robot away from the obstacle. And the behavior of this, the behavior of the external force in these 2 cases is shown by the curve with a continuous line, in which in the second region, the force is equal to 0. This is the experimental setup. I use a Larafy lightweight cobot by Neural Robotics. That is a 6-DoF robot manipulator. Also in the picture, you can see the cobot sensor that I use for validation. This is the video of the experiments and validation. Here, the robot moves randomly and each time collide, it stops. The algorithm is quite sensitive. In fact, for example, here I stop the robot with just one finger. And the robot is capable to detect collision along the whole robot body. For this experiment, I used the combined method, so both the residual at the same time. Here I've shown the residual during the motion of the robot. And for example, this would have been a false positive if I use only the genesis-based momentum. Instead, with the combined method, I avoid this false positive. This is the video of the validation with 4 different speeds of the TCP. And this is a collision with a soft object in which I could easily remove the object after the collision, even if it was clamped. Here are shown the result of the experiment where a collision on the 3rd link is successfully detected and isolated because it generates a peak both on the energy residual and on the first 3 components of the residual vector. Also, you can see that here in the first component of the residual vector at the beginning of the trajectory are present some spikes. These spikes exceed the threshold, and these spikes are mainly due to the fact that the friction model I use is not capable to capture really well the effect of the static friction. And this is one of the reasons why I use the combined methods. Also, the friction model I use, it doesn't take into account the effect of the temperature on the joint, which heavily affect the residual, as can be observed from this slide. And this is one of the reasons why I use the filter version of the residual inside the thresholds. Here are shown the result of the validation. The dashed red line represents the maximum force a human hand can withstand before suffering an injury. As you can see, if the TCP of the robot moves with a speed below than 300 millimeters per second, and the human hand is placed at a distance of 78 centimeters from the robot base, the force generated by the impact are always below this threshold, which means that the robot is safe. And if we compensate the gravity after collision, the static force are 0, which is good from a safety point of view. The plot below shows the influence on the distance between the robot base and the obstacle on the external force. In particular, if we reduce this distance with the same end effector velocity, the external force increases. This is the video of the 2 reaction strategies. Basically, on the left side is shown the stop reaction strategy. So the robot stops as soon as touch the obstacle. In the second case, where I compensate the gravity, the robot bounced back, and this is the reason why the static friction is 0. The static force is 0. Finally, for the contact point estimation, we can follow 2 possible approaches. The first one is a deterministic approach that uses the equilibrium of force and moment on and around the origin of the link frame. The second one is a probabilistic approach. Here, the probabilistic approach used a variant of the particle filter called contact particle filter. Here, each particle represents a point on the link surface. The prediction model is a random walk model, so the particle moves randomly on the link surface. And for the observation model, we have to solve this constraint optimization problem, where the cost function is given by the weighted norm of the difference between the residual and the contact Jacobian response in the external force, where the external force is constrained to lie on the friction cone. So at each iteration, we have to solve this constraint optimization problem as many times as the number of the particles. And the key idea behind the contact particle filter is to find the contact point that best explains the observation. In this case, the observation are the residual, so the estimated external torque. For the modified contact particle filter, I basically remove all the constraints in the previous optimization problem. In this way, I could solve the problem using the weighted pseudo-inverse. Actually, the constraints are in the previous optimization problem are necessary to avoid that the contact point converge on the wrong solution, as can be seen from this image. In fact, the same external torque can be explained by a force that is pushing on one side, but also by a force that is pulling on the opposite side. To solve this problem, I basically initialize the particle using the deterministic method, and in this way, the particle converge always on the correct side. Here are shown the results of the contact point estimation experiments. In the image on the right side, the red dots represent the particles, the green dot is the ground truth. And as you can see, the particles are initialized on the correct side, and after few iterations, they converge close to the real solution. On the left side is shown a comparison between the deterministic method and the modified contact particle filter. In particular, on the last plot, you can see that the X and Y coordinate are almost similar, but the Z coordinate estimated by the modified contact particle filter are much closer than to the real solution than the Z coordinate estimated by the deterministic method. So, in conclusion, in this thesis, I developed a sensorless collision detection method that can be used to reliably detect the collision between robot and obstacle. I also validated the collision detection using an external sensor that reproduced the biomechanical property of a human hand, showing that the robot is safe when it moves, when it's in cobot mode. And I also modified the contact particle filter that shows better result than the deterministic method, which is comparable to the classical contact particle filter, but is less computational expensive and therefore can be implemented online on the real robots. Thank you for the attention.
Any questions? I may comment on something. So my question is, how many particles are you using? And if you're using the fact that the residual, the generalized momentum residual, identifies the link. So you're putting particles only on one link, or you start with particles everywhere?
No. Okay. So with this method, we can estimate the contact point just on the last link. So first of all, we have to identify which link is in contact, and we can easily do this because with the generalized Bayes momentum, we can isolate the link in contact. So if the link is the last link, then I initialize the particles, and I use 150 particles, not too many particles. So the algorithm is quite fast, also because I substitute the optimization problem with the pseudo inverse. And yeah, basically.
Why can't you use it for a collision on previous links?
Oh, it's not possible because in the previous link, the Jacobian is for sure singular. Then we cannot. So when the contact Jacobian is singular, if we have even a small torque generate huge external force, and then the weight of the particle are big, and we cannot get a really good estimate. And this is true also if you are close to a singularity. So if we are close to a singularity, we have the same problem. So we cannot estimate the contact point close to the singularity, even on the last link.
Okay, good. The last presentation is by Damiano Gasperini. So this is a master in artificial intelligence and robotics. and he's presenting the work on real-time instance segmentation and obstacle avoidance for planetary exploration.
Okay. Good evening. My thesis is about real-time instance segmentation and obstacle avoidance for planetary exploration. The work is being carried out at the Space Robotics Laboratory in Tohoku University, thanks to the supervision of my advisor, Professor De Luca, and my co-advisor, Professor Yoshida. The objective of this thesis is to establish an image segmentation framework to give micro-rovers the ability of understanding the surroundings while enabling them to detect, avoid, and segment possible obstacles and features in lunar and Martian analog environments. The main challenge of this thesis is to develop this framework in such a way that it can run at real-time speed on board the micro-rovers, despite their limited hardware's computational capabilities. The swarm robotic platforms on which the experiments have been accomplished is the so-called Clover platform available in the laboratory that consists of a set of four-wheel drive skid-steer rovers. And in particular, the hardware that I've exploited is the Intel VRSense that camera mounted on each unit, as well as the NVIDIA Jetson AGX Xavier GPU board. Two image segmentation techniques have been investigated. The first one is semantic segmentation that is formulated as a classification problem of pixels into defined categories. And this technique is very well suited for doing obstacle avoidance, especially if combined with depth information coming from the camera. The second technique is called instance segmentation that deals with the detection, classification, and segmentation of every instances of objects belonging to a frame. And this technique is very well suited for doing SLAM. And through the visual features extracted, we can make the loop closure component more robust. So since state-of-the-art instance segmentation methods cannot run at real-time speed on board the micro-rovers, I focus first on the semantic segmentation technique and considering an input image representing two non-overlapping objects belonging to the same class, we can see that the output mask can be helpful for extracting instances informations. And the same holds for the second case in which we consider an input image in which two objects are overlapping, they are belonging to different classes, since the output mask from the output mask, we can recognize the contours of the objects. If we consider instead this third case in which the input image is representing two overlapping objects belonging to the same class, the output mask cannot be helpful for extracting instances information since the contours are not anymore recognizable. So the solution idea to overcome this problem is to combine a first step, the semantic segmentation, and in a second step, the depth information to discriminate possible overlapping objects. So a real-time definition is needed for evaluating this framework since the real-time requirement is the very first one. And the literature doesn't give any real-time definition since it's application dependent. So considering that the RGBD camera works at 30 frames per second and the maximum velocity of micro-rovers is 2 meters per second, if we set the maximum displacement between the actual frame and the previous one to 1 centimeters per frame, that represents quite a good reactivity of the algorithm, the real-time definition is computed as the below formula that results into 20 frames per second. Another convolutional neural network for semantic segmentation called CloverNet has been designed and implemented. The network relies on an encoder-decoder architecture that is light enough for running at high frame rate and low GPU latency. The encoder component is designed as a chain of residual blocks depicted on the right of the slide, while the decoder component is designed as a chain of 5 convolutional blocks that are deeply inspired from the segment convolutional neural network. In the next 3 slides, we can see the overall architecture of this network. In each of these skipping connection in the encoder component is representing a residual block, and also from the encoder component shape, we can recognize that this is performing a downsampling operation for extracting high detailed features that are then
fed into the decoder component that is performing an upsampling operation for reconstructing an output a segmented mask. The network has been trained using a new dataset created for developing semantic segmentation models of rocks and rovers belonging to lunar and Martian analog environments. The dataset consists of 1,000 frames extracted from videos recorded during test fields, and each of these frames has been manually labeled through the open source VGG Imageano software. 2/3 of these frames are composing the training set, and after the training, the network has been subject also to a quantization optimization technique. In particular, quantization is the process of reducing the precision of the neural network's parameters. Usually, the parameters of a neural network are stored in a memory as floating point 32-bit precision, but if we convert this in an integer 8-bit precision, we can save memory by a factor of 4. So the direct benefit of the quantization process is that the neural network will consume less memory, but since we are using also smaller representation, the computations will be faster. And so the network latency will be lower, and as a consequence, also the power efficiency will improve. The main drawback of quantization is that there is usually an accuracy loss due to this change of representation. That's why we can speak about the quantization accuracy trade-off, since we need to explore the optimal precision for maximizing the frames per second while preserving accuracy. The network takes as input grayscale properly resized images. The rectified linear unit and softmax activation functions have been used, as well the categorical cross-entropy loss function that matches with the softmax for multi-class classification. The training consists of 50 epochs using Adam Optimizer and the horizontal flip as data augmentation technique for further avoiding overfitting. 5 metrics have been used during the evaluation. There are the accuracy, precision, recall, intersection over the union. That is one of the main metrics for segmentation models, and also frames per second for evaluating the network's inference speed. Several combinations have been considered since the GPU board offers us 3 quantization precisions. There are floating point 32-bit, 16-bit, and integer 8-bit, as well as there are 2 power modes for the GPU board that are the 30 and 15 watt. And so as a result, we have several combinations each for which we can run the evaluation. And this table shows the results for the 30-watt power mode of the GPU board. If we consider the class-wise metrics, we can see that there is always a drop of performances of the rover class with respect to the rock class. This is because the network has been trained using a dataset that is a bit unbalanced for the rover class. While if we consider the average intersection over the union, we can see that the no optimization mode value is the same for the floating point 32-bit optimization. And again, this value is the same for the floating point 16-bit quantization and optimization strategy. This is an excellent result since the floating point 16-bit quantization is showing not to affect the prediction metrics. In particular, there is no accuracy loss, while there is an improvement in terms of frames per second. On the other hand, if we focus on the integer 8-bit quantization, there is always a drop of performance in all the 5 metrics, while for the frames per second, the optimization mode is not real time for the Clover system, while if we apply an optimization and quantization strategy, we can see that the network is running at real time on board the micro rovers, and the smaller the representation, the faster will be the frames per second. On the second table, we can see the results for the 15-watt power modes. The results are slightly different, but almost the same. And the main difference is that the frames per second for the floating point 32-bit optimization is not real-time distant for the Clover system. On the left of this slide, we can see 2 sample frames. While on the center, there is the corresponding grayscale image, and on the right, we can see the output computed by the neural network, while in this other slide, we can see 2 videos showing the performance on a real test field computed by the network. After the CNN development, I moved on with the implementation of an instant segmentation pipeline, and the first step of the pipeline is the error thresholding. And the first step of the pipeline is the area thresholding step that takes as input the segmented mask and will draw the external contours of each segmented object. Then a rectangular approximation step can be carried out for computing the smallest rectangle containing each external contour. Once we have the rectangle's coordinate, we can also compute each area, and the areas can be thresholded in the thresholding step that aims to select the largest area represented in this frame. This thresholding step is performed because of three reasons. The larger is the area, the higher is the probability that an area is representing a good landmark for the SLAM algorithm. The second reason is that the larger is the area, the higher is the probability that an area is representing overlapping objects. And the third reason is that we want just to further analyze the largest areas because we want to further improve this pipeline efficiency. The second step of the pipeline is called depth thresholding that takes as input all the selected largest areas by the previous step, and will aim to draw possible internal contours between eventual overlapping objects of each area. This is done by thresholding the depth information corresponding to each analyzed area. And this is because, as already mentioned at the beginning of the presentation, the depth information is helping us to discriminate if an object is more on the front or more in the back. And so we can discriminate possible overlapping objects. After the prediction, we can merge the result with the segmented mask. And in this step, we can store the contours coordinates. We can compute bounding boxes containing each instance, and we can assign to each instance a label with the predicted class and with an ID for identifying each instance. The results are showing that this pipeline is real-time for the system, and also there are good results in terms of intersection over the union. As a final step of this thesis, I designed an obstacle avoidance SLAM system integrating the image segmentation framework presented in the previous slide. In particular, the obstacle avoidance component is taking as input the segmented mask by semantic segmentation with the corresponding depth data. And superimposing these two information, we can create depth mask segmented that can be converted into a ROS/scan message. And this type of messages are then fed into the ROS navigation step for composing the cost maps. They are for obstacle localization, and they are useful for computing obstacle-free paths by the path planner. On the other hand, the information computed by the instance segmentation pipeline can be fed into the loop closure component that can update and query a local database for doing landmark recognition and pose a map correction for the SLAM. As a conclusion, a real-time definition for the Clover system has been provided for evaluating the framework. A novel convolutional neural network for semantic segmentation called CloverNet has been designed and implemented, and it is also optimized and quantized using the GPU board, and the network can run at real-time speed on board the micro rovers. The floating point 16-bit quantization optimization strategy shows excellent results and showed that it's now affecting the prediction metrics while significantly improving the frames per second metric. A novel real-time instance segmentation pipeline has been designed that is working combining the semantic segmented mask and the corresponding depth data. And finally, a system for obstacle avoidance SLAM has been designed at high level for that integrates the developed image segmentation framework. Thank you for your attention. So, do you mean for doing semantic segmentation or instance segmentation directly with it? So, yeah, there are methods for they are considering RGBD frames But the point is that usually these artificial intelligence convolutional neural networks are too heavy, too large, too deep for running on board this edge device. And so the results is not showing real-time performances. But yeah, I've considered the option. Real sense. So yeah, the point of this pipeline is for doing SLAM. Yeah, of course, the sensor doesn't provide information at a long range. For that information, we could consider like LASIK and other sensors. But yeah, for the moment, this was the hardware available in the laboratory.
Ok, thank you. Allora, adesso vi devo chiedere di allontanarvi, vi richiamiamo. No, no, guarda, facciamo così.